happening again. We're doing another Gimbal stream. Oh man, there's Tuco. I thought he was just gonna be all chill, and now he's like, meow. Tuco, did you hear that the stream is starting and now you want extra attention? Meow. How's it, little fuzz tiger? Oh, he just wants the head rubs now. Just getting stuff started here. Actually, this might be a good opportunity to update the topic line. It's still old, as you can see. That cat is such a good cat. He's basically the reason I want an awesome mobile camera in this space. I want people on the internet to have more opportunities to interact with this amazing little fluff tiger. Let me reset these two USB hubs. There we go. Barrow. So, we are no longer fixing this gimbal. This gimbal is now fixed. For a little bit of backstory, this is an effort to modify an off-the-shelf quadcopter gimbal for use in a robot that you can all fly around in this huge space over the internet to interact with my crazy cat. And in the process of that, I got a little bit into experimenting with some, at the time, unknown commands, and ended up messing up the stored parameters, which was a big problem for a while. The gimbal would just turn on and then immediately try to break itself. So we managed to, with the help of decrypting the firmware and investigating what goes on between the firmware and the Windows tool and just a lot of head scratching, we know enough about it now to recalibrate it from scratch, at least pretty close to from scratch as far as I can tell. And we're pretty close to having enough info to control it properly over this new serial protocol, which should let us... the thing that I mostly wanted to get that wasn't available through the original kind of RC servo style interface was the ability to have some kind of absolute notion of where this is headed. So ideally, having some feedback from the magnetic encoder on the yaw axis on my own control loop, which handles like processing user controls. That's kind of what I wanted. And I was about ready to add a separate wire just for tapping off that signal and using the original joystick pulse width modulation style input. But now that we're at this point with all of this reverse engineering behind us, I can actually just keep the gimbal in a mode where I can read and write its control loop parameter space over serial. And while doing that, I can just, turn off the yaw following loop and then directly set the output to give it a speed that I want. And then I can read back the current position from those magnetic angle sensors to figure out what the heading of the camera is relative to the robot, despite the stabilization and the speed control. So that part is actually working pretty well. I've hit a little snag on controlling pitch, which is related to, I think, an incomplete understanding of how the original firmware handles that. So that's kind of the direction this investigation is going to go. So Mini 3D gimbal reversing, Homebrew control tool. So one open question still is, are we going to need to patch the firmware? I was at first kind of against patching the firmware since it seemed like kind of a maintenance headache, and I didn't think it would be necessary. It looks like we can do everything we need over the original serial protocol. And I think that's probably still the case. There's one thing that might be easier if we could patch the firmware, but I think actually the main reason that we might end up wanting to do that is specifically, I don't have to only have back of head camera. I think specifically the biggest reason I think to maybe patch the firmware is to get this thing to always come up in the mode where it's listening for serial commands. By default, it seems to go through a few states as it boots up. It seems to have a first state where their own serial reflashing bootloader is listening for commands, and it speaks one particular protocol. Then it goes through a different state where after that times out, it starts booting up the actual Gimbal firmware, and that sends out like a hello packet saying, hi, is there a computer there? And if we respond to that within its timeout, then it'll continue listening for serial commands. If not, it appears to just turn off the serial port and only listen for pulse width modulation inputs on those same pins. So currently, my best solution for dealing with that, effectively what this means is that you have to have something listening on the serial port before you apply power to the gimbal, or it'll get stuck in this mode where you can't talk to it. And it's possible there's a way to command it out of the PWM mode. That might be something we can look for in the firmware. I'd be surprised to see that, since I just don't really quite see how they'd handle it unless there's some way of just sending like a super long PWM command or something, like putting the serial port into break state for a certain length of time or something. There might be something like that, but I think it's unlikely. And so we could go digging for something hidden like that, but it might also be pretty easy to patch it so that it always, like maybe it just never times out. Maybe maybe we like synthesize a fake I'm a PC response in the first MCU, because we do actually need all the MCUs to go into this state. The architecture on this gimbal is actually pretty interesting. It's almost like they had this like 3-axis vectorized system, and then they just like compiled it. Okay, the x-axis goes onto this chip, the y-axis on this chip, the z-axis on this chip, and there's there's some control logic, for example, on the final microcontroller, the one that actually reads the IMU. This seems to be specific to that one. There's some logic on the first micro that actually handles the joystick inputs from the RC servo receiver. But most of the code seems to just be roughly the same skeleton, but compiled with different options. So it's like they had this code, and like at compile time, they just like slide off the X, Y, and Z chunks of this to different micros. I think it's pretty cool architecture. I don't know, like, I get so, this is going to be like a tiny, tiny micro rant, but I get so annoyed with people just like being like scoffing at like Chinese products for being like badly made or something. This thing is all Chinese. It's designed, I don't know where in China, I don't know that much about them, but they seem to be like really good at what they do. And I think there's so much attention to the really low end of like, well, what can you buy for like $1 on eBay, that people just ignore all the like really, really awesome design that's happening all over the world. So I think this is a really good example of a product that's like completely made and designed in China that is just, everything about it seems really well made. Which shouldn't surprise people, but I guess some people are surprised by that, so end of micro rant. Anyway, the gimbal seems to be working pretty well now. So we can, I want to just stop talking for a bit and show you what I've got, and then we can decide whether or not to do the patch. If we are going to patch the firmware, then it would be helpful to, there's like one last little bit of it that we need to understand, which is like how to recalculate the CRC in the firmware, which I think is pretty straightforward, but we just need to like have code for that handy. And I might as well write my own firmware flashing tool so I don't have to get a Windows VM out just to do that, since I have a logic analyzer trace of the firmware update, so we can see how those commands work. And of course, now we have the key necessary to re-encrypt our own firmware images after making any modifications we want to make. And this thing, I don't know. I think part of the problem I'm having is that I think maybe the way that they internally customize the firmware for different control modes is just by making compile time changes. Because if you go to the website, you can download different firmware blobs for these two different control styles. They call them rocker speed mode and rocker position mode. I think by rocker they mean like the vertical stick on your RC transmitter. And I think I haven't actually analyzed the speed mode firmware yet. I've been just looking at the position mode firmware, which is what I'm using, but I can kind of see already where they would just like slot in two different chunks of code. And I haven't seen a good way at runtime to just kind of like disable all of that and do it externally, so that might be something to poke at. Oh, nice. Michael Udaltsov has already figured out the CRC. Yeah, I should mention that they've actually done some cool research, which is in a GitHub branch off of mine. Some interesting cryptanalysis on the blocks and looking for commonalities. Okay, yeah, same as the CRC that we're using for the short packets, which are used in the everyday firmware instead of the bootloader. Okay, let's show off what we got here. Oh no, is my video grabber in need of a reset? I'm sorry about that. Restart little video grabber. There we go. Oh, okay, the long form. Yeah, that would make a little more sense because that's the one that seems to be used by the bootloader. It's interesting that they just seem to differentiate the bootloader and the normal protocol by kind of like switching up the CRC in the header a little bit. Like they wanted to intentionally make them incompatible from each other, you know, maybe to prevent mistakes. So, actually, in case you want to play along at home, there's a GitHub repo with everything we've been doing so far, if my keyboard even works. This is the same USB issue I was complaining about last time. I just haven't had time to fix it. So GitHub/scanlime/FY Gimbal. Everything we've been doing is going here, with the exception, of course, of actual firmware dumps, because like that stuff is lawyer bait. You want to download that from their site. But if you have a firmware dump, there's starting to be some tools here for experimenting with it. So if you go to the firmware directory here, there's an unpacker. We might have a packer soon. There's a tool for extracting defaults. And I think if you go to the forks up here, yeah, you'll see Michael Udaltsov has a branch up here. And this one has some more investigation into the firmware. Yeah, so this is also another fun starting point. So this was something we didn't really know much about this. Like I hadn't really gone into that much detail on the stream, so Michael did a bunch of analysis on the firmware too and discovered like the rough structure of the file and looked at the differences between all these different versions, which is pretty interesting. So this is something I haven't done at all. Like I've only been looking at this binary right here. That's the one that I've been looking at, but all of these other ones are available that seem to be the same basic system. I mean, these are the same gimbals. I think this is a different model gimbal that runs on the same system. And this was really one of the things that tipped us off onto what the encryption type was. The repeating 1 kilobyte blocks, also some mentions of AES elsewhere in the Windows software. Oh, interesting. There's yeah, a couple different forms of that AA55 and 5AA, etc. Like as Michael's saying in chat. So yeah, this is super interesting. So once we got and then as far as the key went, that's just something where I happened to make a RAM dump while we were experimenting with the serial wire debug port. And that's here in the pile of traces here. And just hanging out, was it here? Oh, I'm still in I think that's in this repo. So yeah, if you go to traces, this RAM dump right here, I just happened to make that while we were playing with the debug port. So this is from my gimbal, which was misbehaving, I think while its motors were off. So probably not super representative of the state of, you know, a working set of control loops as they're doing their thing. But it happened to have the encryption or the decryption key in it. So using that, managed to make a little unpacker tool that can get us plain text for all the firmwares, which is this critter here. And so now we have these MCU 01 and 2.bin, which I've been looking at in IDA. And so we'll go a little bit deeper into this in IDA in a sec. Oh, Tuco, that's not a good thing for you to be digging in, little guy. Whoa, cat. Oh, you're so sharp. Okay. Yeah, so let's save IDA for later. So here's what I've got so far. I've separated some of this out into other modules. So like, there's now a shared module for that WebSocket server. So I think I'll be able to run the GUI. Oh, where did my mouse go? Stupid ground loop problem. So I haven't actually tested any of this yet, but I think I'll be able to run this WebSocket server in the background while I run this thing in the foreground, which looks at looks at the control stick on this Xbox joystick, and I'm trying to map the right control stick to yaw and pitch, so we can actually fly this thing around. So let's show you the current state. I already got a console on the gimbal, or on the Raspberry. Okay, so the gimbal's off right now. Here's all the software we have. I think that's all checked in. So let's just start with controller. So it's going to start listening for that hello command and getting ready to respond to it. So I have to run this and then power on the gimbal, and then it should wake up basically. So server's running. Okay. And now this is running and pulling the joystick. That's interesting. The motors don't seem to be on. Did I break something? I thought I might have seen something fly by. Let me check the text output. So that did end up running the WebSocket server. Let's just try the WebSocket server by itself. I've tested the joystick thing by itself. Yeah, that's working. Okay, waiting for gimbal. Okay, connected to the gimbal. And can we connect to the WebSocket server? Ah, there's our bug. Well, one of the bugs. So this is using the Python WebSocket server for Python 3. It's pretty neat. It's all async I/O. All the gimbal stuff is still blocking, so this gets run in a separate executor. But at least this little snippet of code here gets to be nice asynchronous code. Handle client. Oh, these are just missing self. They have no sense of self. What will they ever do? So once the gimbal has already been kind of halted and kept in serial mode, we can tell that it's listening by just sending a test read with a very short timeout. And if we get a response, we assume the gimbal's already running. We can continue the existing connection. Okay, now this is working, I think. So you can see the sensors are reading as I move the gimbal around. If I click this, the gimbal springs to life, and the graphs kind of start settling out, and then it should be stabilizing as normal. You might also notice it's not following. Well, let me turn on the other camera and then maybe you will. Welcome to the other camera. So I think you might first notice that it's holding steady, but not at a centered location. I think that that's just a pretty arbitrary location that it powers onto, and the thing that usually commands it toward the center is the heading follow loop, which is currently disabled. So this is just kind of the default mode. If you break into its normal startup, then there's maybe some slight exceptions to this, but mostly all I'm doing is breaking into the startup and turning on the motors and then letting it go. There's a couple of other auxiliary things that I found are useful to do, like zeroing out the current velocity, these control rates in parameter 3. These are the outputs of some of the control loops, like the follow loop. But when those follow loops are off, then this will directly command the gimbal velocity. So that should be the state we're in right now. So if I command the yaw control rate right now, this should directly move the gimbal. And it's pretty smooth. This is just controlling the angular velocity that it's trying to hit on that axis. So there are other control loop layers below this that control the motor that operate faster. But I think this value here, 3, which is then integrated into 8, I think. Actually, 8, I think, is updated only when it's stopped, so 8 might be weird. But 3, I think, is mostly the output of the slower control loops running on timer 4 that we found in the firmware. So right now, with the follow loop off, I can just kind of steer the gimbal around like this. And so this is how my joystick controller has been operating so far. And if I turn on that follow loop, which if I set this axis to 1, whoa. So you can see there was an impulse on that control rate, and then it settled down to around 0. So now it's driving. And it's actually settled out to mostly straight on. I think we're going to see it follow now. Check that. And you can see the waveform of the actual follow motion. And you can also see it's got like a linear, I think it's like a piecewise function where depending on how far away it is, it has a couple of different speeds that it goes to. I should be recording here. Try to move this around without the squeaky pan of ice. We'll be able to look at this in more detail once I have this free of some of the wires here. Part of my goal in making this a little embeddable WebSocket server is that I can run this even once the robot is actually constructed, so that I can just look at the gimbal parameters in any state of builtness here. So that's my hope. So in this state, if I were to actually touch this, then it might occasionally cause the camera to briefly jerk around, but mostly this has no effect because its control loop is overriding that. Um, 8 here, I think I also probably don't have a good reason to set this. That's like, I think it's the current estimate of where it was pointed last time it was stopped, but I don't know much about the coordinate system here. It seems to be pretty arbitrary. It might just be something that kind of wraps around arbitrarily. See, so one thing that you can do is, since all of this is just like a shared pool of RAM that all the control loops are reading and writing that you can also read and write, you can see, like, if you're sending something but it's also being overridden by something else, then you can see like little impulses get through. So like if I move this, you can see it kind of jerk back and forth a little. Maybe hear it. And you get a similar effect if you try to set these control rates for pitch. Not quite at the same time scale, but if I give it a speed, then you can sometimes see a little vertical nod get through, but mostly it's returning back to a set point. So I took a little closer look at that, and it seems like there are two different versions of this control loop that are selected between, depending on whether or not you have this follow mode on or off. Both are actually setting the this control rate, they just do it in different ways. So maybe let's see if we can illustrate this. So right now I have follow on for yaw. I haven't actually looked to see whether the roll firmware even cares about the follow mode, but I don't think there's a way to turn the, I don't think there's a difference between these settings for roll. Like, I don't think that has any effect. But then this one should be the follow mode for pitch, which selects between those two different loops. So right now in follow mode 0, I think it's just trying to track the horizon at this point. So it's using its, I think this is based on its neutral calibration, so facing straight forward, with a correction based on the angle from the gyro. So the effect of that is to hold it at a level horizon. And it does so pretty much immediately. Like it isn't kind of trying to approach it with a very slow motion. It just goes straight to that commanded position. And so that mode is actually really straightforward. It's just like subtracting those two values, and then I think it does a little bit of like clamping and cleanup on that value to turn it into a rate. But it's mostly just a really simple proportional control loop. The trouble is the two values involved are just the current, I think it's the current angles, which are just updated continuously, and the center calibration, which I don't want to change dynamically for a number of reasons. Like I don't want it to be saved accidentally because that would mess up the calibration. I think other things rely on it. I think the change we want to make is not necessarily in that coordinate system. So several reasons not to do it that way. So I don't think I want to use this version of the control loop for the cat cam as much as it seems to be pretty simple and to the point. Let's take a look at the other version when we set follow mode to 1 in that axis. So you might have seen that move already. Let me try to illustrate the difference. So that's the neutral heading in follow mode 0. This is not the mode that it usually runs in, I think. I think usually when you boot this thing up normally, the follow mode is on for all the axes. So here it actually is aiming slightly downward, which is what the gimbal normally does. And I think in this mode, what it's doing is it's following along with changes in the motion, but it's also applying an adjustment from the joystick input. So let me see if I can illustrate what happens when I just tilt this. So let's do a side-by-side comparison. So this is what happens in follow mode 1. When I tilt this, the camera tilts pretty quickly, and then there's also a bit of a lag where it kind of settles into position, but it seems like it's mostly following what I'm telling it to do. One variation on this might be to have this loop on, but have the rate set to 0, because I think I might be able to do that. I don't think I have it on this dashboard quite yet. But we could add the follow rate to the dashboard. That would be a good addition. So yeah, so that's not quite what I want, but it might be a basis for getting there. Let's switch the follow mode back to 0, which is the one that I don't have much control over. So now it's just like totally stable, planar to the ground. It's like a chicken head or whatever they say, or like a pigeon. You just move it and it just keeps that horizontal orientation, which is nice, but I don't think we can easily apply an offset to this, which is not quite what we want. So in this mode, let's add speed to this dashboard and see if we can get the effect we want by using this mode but setting the speed to 0. Oh, let's also, so I want to add that to the dashboard. I also want to get the joystick input working, because that's part of what I wanted to show here. Which one is follow rate? 65. I want something kind of like this, like a really tiny graph. This one's a little bit too tiny. Let's make these like 20 pixels high. And these should go from, say, 0 to like 1,000. I really don't like how repetitive and error prone this is, but I haven't bothered to add another layer of abstraction. There's probably some JavaScript library that would just like do the exact thing necessary to make this cleaner. Okay, follow rate. And I still have the follow loop on for the yaw axis too. Let's just, for consistency, turn it on for... Also, I don't think follow mode has any settings other than 0 and 1, so let's just change that slider for convenience. I just had it set to max so I could explore, or max to 10 so I could explore other values. Okay, so these will all be on. And the rates... Let's just set them actually to 0. I think 0 might set default. That's interesting. Let's take this out of the mount. Yeah, maybe 0 is special. Let's try just something very low. I think there might be a minimum in effect. What if we set this to something really higher? Is this not controlling what we're supposed to be controlling? Maybe I made a mistake in the numbering. Let's check it over again. So that's 65 here. Yeah, that should be 65. It defaults to 900. I mean, we could probably go faster than that and see what that's like. Let's try 10,000. I mean, as a maximum. And let's just... I mean, we've got feedback that, I mean, if the graph changes, then we know the parameter got all the way to the device. That's our readback. So what if we set a really fast yaw follow rate? You know, I wonder if that's a maximum velocity, and maybe it's hard to actually test that effectively given that I can't really move that super fast with all this stuff attached to it. Not being able to set this to 0 is kind of annoying. So that might just be another thing pointing toward let's patch the firmware. But okay, let's try the joystick again. So that was just the standalone WebSocket server. Also got this thing that takes controller input and also has a WebSocket server. Is this still working? All right, I think that's still graphing. Is this still operating? Controller probably needs to be on. Whee! So I made it super sensitive by giving the controller a pretty generous dead zone and then having a really nonlinear speed ramp after that. I think it feels really good. So you can go really, really slowly here if you want. Let's hook the video output up to the streamer so we can see it. Oh, excuse me, Tuco. So this is just trying to be subtle about it, but it can also go fast. If you go really fast, you can slam it into the end stops, which I would avoid doing, but I added a really crude limiting, so if it notices that the magnetic sensors are outside a particular range, it'll refuse to send speed commanding it further out of the range. But it's not foolproof because you can just like accelerate your way into the end stops and it can't stop you. So yeah, that's hitting my software end stop. That isn't hitting the hardware end stop. So I'm pretty happy with that movement. And this is with follow disabled. So if I move this around, so for example, the robot's kind of shaking around, that will not affect the heading. The heading is only going to change when it's being commanded to change, which is what I want. So the robot's moving around, it maybe gets into some kind of weird angle and it just kind of sits there and that's fine. And then this should still work the same way. I'm seeing the video kind of jerky on this monitor, but I think that might just be the preview not getting every frame. And this actually seems to work pretty well, even with a good bit of like tilt in this platform. Let's get another angle. Oh, Ken says it's a little jerky there. We could try full screen video. It might be the compositing dropping frames on this end. I think we need manual focus for this shot. Yeah. Let's check that out full screen. Well, fuller screen. Oh, that is smooth here. Kind of. Maybe a little jerky here. There might be some frame rate difference. It's probably fine though. I think the gimbal is fine. I think this is just a video issue. Hello, other camera. If only we could aim up. So that's really the next thing. Yaw is doing what I want, but pitch is not working. And we can look at why pitch is not working. Pitch is pretty different here, and I was trying to command it by sending it kind of fake joystick packets, the same as the third microcontroller would normally get from the first microcontroller. And so far I haven't been getting much luck. I know the joystick packets are getting through, but I think it's not in the right mode for them to have the intended effect. This is going to be really fun to drive around the whole shop. So, get this out of the way and let's go into the code a little bit more. Oh no, my coffee. I spilled coffee on the gimbal's fake USB to USB adapter. That's terrible. It's not really a USB to USB adapter. It's a USB to fake USB adapter, which is about as great as it sounds. It's actually a USB to 3.3 volt serial adapter, but they decided to use a micro USB connector for that for some reason. So everything we've been doing, talking to the gimbal, like you could do this through the serial cable that they supply for doing firmware updates. I've just been using the Raspberry Pi here since that's what I plan on doing for the robot that I'm putting this in. But you could totally just run all of this in Windows if you wanted, I think, if all the Python libraries work right in Windows, which they should. It just uses PySerial and some Python 3 standard library stuff. The joystick thing is Linux specific, but the rest of it should work on other OSs. Oh, someone's saying that my portal mug doesn't have a, like, you can't get these anymore. My friend who I was helping move last week has one of these too. I think he's moving with it. Don't know if we knew that they were so rare. So yeah. Let's take a look at why pitch and yaw are different. Michael in chat says the S in USB does stand for serial. The adapter just ignored the U and the B. Yeah, that's pretty accurate. So we can actually see that. So this is something I haven't really looked at yet. Is while the joystick controller code is working, we can look at the parameters here and see them in real time, which is pretty cool. So, for example, when I move the joystick left and right, I have the joystick pretty much directly mapped to this control rates here. There's a dead zone in the middle, and then you can see that it's nonlinear. So if I push it slightly, you can see a small rate there. And then if I just push it more, it gets significantly higher. The other thing that was interesting is this 8, I think this is its best kind of integrated estimate of where the gimbal is pointing in an absolute fashion, but it's in like a kind of arbitrary coordinate system that wraps around as much as it wants. So like you can watch this to get kind of an idea of where the gimbal is pointed in the yaw axis, but it's like I don't really know specifically what it would be reliable for unless you just want to measure relative positions. Then what else we got? This is a bunch of stuff I haven't documented. These are the actual angles from the magnetic encoders. These are both related to the motor power, but I'm still not quite sure what the differences are. I haven't looked at that section of the disassembly. So all of these are numbers. These numbers are slots in its parameter space, which is just a collection of 128 signed 16-bit integers. And these are used as kind of tuning parameters, things that are saved persistently in flash memory. They're also just used as internal state for a lot of the control loops. I think this was just a convenient way for the designers of this gimbal to get parameters out for debugging, pretty much exactly like I'm doing right here. And in most cases, one of these slots is used as a vector with the pitch, roll, and yaw components being distributed to the 3 corresponding microcontrollers. Some of them are, well, even things like the follow mode, for example, are Boolean vectors. It's a vector that exists separately for each of the 3 axes. There are some things that are going to be specific to just the 3rd axis. I haven't really looked at what most of them do, but if you look at a region of the memory dump in the parameter space, you'll see a bunch of stuff that's 0 in the first 2 axes and non-zero in the 3rd axis. The yaw that this is reporting is based on the angle at the yaw magnetic encoder. So you can see here it's drifting some. I think that would just be related to gyro drift mostly. If you wanted to hold it at a particular location, you could have kind of a gentle control loop that does that on the PC side by sending speeds to the underlying control loop. The speed inputs that the next level control loop take from the follow mode control loop seem to be a really convenient place to inject my own inputs into this. Alistair asks, does it recalibrate each time you start it? Otherwise, you could translate back into real-world coordinate systems. I don't think there's any kind of absolute reference. Like, I don't think this has a magnetometer as far as I know, and even if it does, they aren't especially great as like absolute angle references. I think my best bet for an absolute reference is going to be assuming that the robot is in roughly the same orientation relative to the room, or at least that I can calculate that orientation pretty easily. And then using that yaw, like this kind of first joint in the gimbal, I can just read its sensor to figure out where the camera is pointed relative to the robot body. I think that's what I want, but it isn't necessarily the only thing. I mean, and that's kind of like what the follow loop is doing. I just kind of want my own policy embedded in that kind of thing. So I think that seems like, so far from what I've seen, that's a nice place to cut this logic, is to put the stuff that would normally be doing the heading following, to like kind of replace that with my own logic, and then to keep the lower level control loops pretty much as is. So you can see that the current position here is just straight from the magnetic encoder, so it changes when I command this with a speed, but it'll also change if I just move this. So, and there are several different ways that you can measure angles and the current state on this. This is just the way that seemed most relevant to the robot that I'm trying to build. And then for the pitch here, this is a lot higher level. This is something where I'm simulating the input that would normally be sent from the servo PWM receiver to that 3rd microcontroller that's kind of implementing the joystick inputs. So this number is actually, I think it's in just units of microseconds. I think this is being measured by the first micro usually, and then sent on to the other 2 micros in this command 1, which is like a joystick packet basically. So here I'm just using the joystick to give me a speed, which I'm integrating myself in Python, and then just using that to change the effective position of that tilt stick, which with this particular firmware should just map directly to an offset up and down to the camera's pitch. But as you can see, it isn't working. I can show you how it's supposed to work. Well, how I thought it might work, at least. None of this is supposed to. All of it is investigation. So this is the body of that controller we were just using. So we're turning off the follow loops everywhere. I think that's not what I want, actually. I think we just showed that with the follow loop off on the pitch axis, it isn't going to be responding to the joystick, which isn't what we want. So let's turn it off on yaw, but turn it on for the other two axes. We're zeroing out the initial velocity, turning on the motors, starting up our own default pitch based on the two limits that we have set. So this is just calculating a pitch and yaw in appropriate units based on what's coming in from the joystick. For the yaw, we end up reading the magnetic angle sensor here, and then setting the speed. But we're setting it only for yaw. We don't want to touch the speed from the other two micros, because otherwise we're going to clash with control loops that are also writing to those variables. And you'll end up seeing little jitters as we end up zeroing something that should have had a non-zero value. So that's why we're writing not a vector value, but just the yaw component. And this is just the very simple braking action that I was demonstrating. So the joystick packet, it seems to have, well, so the joystick packet, it seems to have a handler on both microcontrollers 1 and 2. So if you send the joystick packet to the, directly to the yaw microcontroller, it'll ignore it. It has no handler for it at all, because usually it's the one generating those. But if you send them to the other two microcontrollers, they each know how to do something with it. Normally they seem to daisy chain, like the first sends it to the second sends it to third. But I think you can also send it directly to the third microcontroller, which is what I've been doing so far. And it has 3 16-bit integers and this 1-byte mode parameter. The first parameter seems to be pitch. The next two seem to be related to yaw. I haven't sorted exactly what this is, but I think one of them is like a target yaw and one of them is like a current yaw or something like that. But I think they're not important in the case of this last microcontroller, at least that's my working theory. So I'm setting this, this looks a lot like the packets that I've captured on the wire, but with a couple of changes. Mostly I'm targeting them at this last micro. And I've also been trying other values in this last byte, the kind of mode-like thing. So I think 1 is the mode that this is supposed to have, at least as far as I can tell from context. But another value that I found interesting here is to actually set this to 8. I think there's a flag in that third bit which maybe does some kind of control loop reset on that micro. So this won't operate correctly, but it will operate differently. Hear that? Or even see the vibrating? There's kind of this ticking noise. And I think the ticking is actually an impulse being generated every time we send that joystick packet with that 8 set. And if I kill this, then the ticking will stop. But the gimbal is still running. So I don't know if this is related to anything operating correctly, but that might be something to keep in mind. I'm going to set this back to 1. Let's go back to the 2-go cam. I don't think we need the gimbal camera right now. High-tech input switcher involving moving the BNC cables around. Oh, Ken says if you could detect the end-stop hits, you could calibrate against that. Very true. I could definitely write something that would do that. I could just gently move up against the end stops and find them. I don't know how much, well, yeah, I probably do care about detecting the end stops. I was thinking that maybe there'd be a slightly higher level control where instead of just protecting it from bouncing against the end stops, I would set like a range, like a keep out zone as far as like overall room coordinates, but like that could operate at a different level. Like that could operate in terms of room geometry rather than just the angle of the encoder. Oh, good question from Sodium, who says, I just got here, so you may have mentioned this already, but have you taken a peek at the alternate control mode firmware that they offer? So I haven't opened that one up yet. I'm pretty sure I know what I'm going to see in it at this point, but we could definitely look at it. I have come across the code in MCU2 that seems to be where they would slot in different control algorithms. And it seems pretty straightforward. So like we could look at what they did differently, but I think it's going to be pretty unsurprising at this point. I don't see a way to turn that code off, so it might be really interesting to patch the firmware and try just disabling that section to see if we can, generate a pitch speed ourselves without that loop turned on. I'm not sure that's what we want, though. I think what we want is that mode we were seeing where it's stabilized really nicely, but with an offset. But I'm not entirely sure which control loop is responsible for that stabilization yet. That's maybe something to look at. So let's hop into IDA. So I've been looking at all three of these firmwares to some extent in IDA. I've kind of gone the deepest into the first one, since it's related to the communication directly with the PC. So let's open up maybe MCU0 and MCU2. This is still running in my VM that has a broken Python because my other VM is running Windows updates right now. Okay, so this is MCU0, aka the yaw axis. And we just landed right here in serial one handle read. Let me add addresses here for reference so that people can play along at home. Yeah, so these are addresses in firmware 1.15. Let's just turn. I really like having all the toolbars off except for the navigation view, but I can't be bothered to go through and tick all the tech checkboxes except for that one right now. Okay. So there's a good amount of stuff in this firmware, but so if you're looking for the way to get here, actually, it's pretty straightforward. We started out with the interrupt vector table. So first of all, just after we got the flat binary, figured out kind of where it should be loaded by looking for a correlation between addresses in the interrupt vector table and start of functions in the code. And so there's kind of a limited number of those to check because the bootloader is probably going to be a multiple of the flash block size. So it turns out the bootloader occupies the first 16K. And then this image gets loaded at this address, 8004000 hex, which is 16K after the beginning of Flash. So if we go there, that's where we've loaded this in IDA. And then we can just start following all these references that come out of the interrupt vector table. And if we want to know what these are, we can just look at the datasheet for the processor. These are all, like, the first part of this comes from the ARM Cortex-M standard. So there's the top of stack, there's the reset vector, which in this case is a little entry routine before main. There's some fault handlers, which are all just infinite loops here. And then here's all the interrupt controller targets. So I think if you look at the nested vectored interrupt controller and the STM32 documentation, you'll find everything you need to know about this. And the STM32, you can just look at its list of interrupt vectors and kind of label all the ones you want. And you can see 2 serial ports in use, and an SPI port, and a bunch of timers. You can start pulling on all of these threads. Some of the really interesting ones so far, timer 4 is handling all of the kind of higher level control loops, like the follow loop that we've been taking a look at. UART 1 is the incoming UART, like from the PC or from the previous microcontroller. UART 3 is the UART going to the next microcontroller. So in this case, UART 1 is talking to the PC at 115 kilobaud, and UART 3 is talking to the next microcontroller at 2 megabaud. So if we look at this, either of these aren't going to be super interesting. These are just filling up FIFO buffers with the data coming in from the UART, but they'll tell us where the FIFO buffer is located so we can find the other code that processes it. So if we go to USART1, this just has another jump here to another function. So this is the actual ISR. And this has a critical section here where it's clearing interrupts, storing something in a data structure, restoring interrupts. And if you kind of look at what's going on in this data structure, you'll see this byte-wide store, storing a byte that we got from the serial port data register up here, which is based on the serial port base address, storing it in something calculated based on this FIFO buffer location. So you can kind of put the pieces together and see that this is a pointer to a FIFO data structure that keeps track of incoming data on that serial port. This is just a thing in RAM that we've given a name to. It's hanging out at some address. We don't really know what's in there. It's just a reserved location. But then, if we start following this, we'll find it used in a few different places. This call site up here turns out to be pretty boring. It's just initialization. But then this one down here turns out to be a polling function. This gets called mostly on the main loop. I think only on the main loop, actually. But it's going through and similarly, it clears interrupts and does a little critical section on the data structure, but this time it's pulling out bytes. You can see this byte-wide load, which is a pretty good clue. And if you look at where those go by following R5, they go right into this function, which I've been calling serial1 handle read. Then this is starting to look a little bit bigger. In this microcontroller, actually, serial1 handle read is pretty simple overall. First, there's a state machine, which just handles the packet structure that we've been seeing. So you can just kind of follow the case numbers. They go up from 0, basically. And this might even be easier in flat view rather than graph view. So case 0, it's looking for this byte in the header A5. Case 1, it's looking for the next byte, 5A. Then you can just see it's kind of pulling out each portion of the packet bit by bit until finally in state 7, it's done with the packet, checking whether the CRC is any good, checking whether the packet goes to the current microcontroller or a different microcontroller. If it goes to the different microcontroller, then there's another function that kind of stores and forwards that whole packet for the other micro. But if it is for the current micro, then in this micro, actually, there are so few commands we're handling that the packet handler got inlined. So this is actually conceptually kind of a different function, but it got inlined by the compiler. And this switch statement keeps track of all the different commands supported by this micro over the serial. So then we can start to correlate this back to what we know from seeing the serial traffic between this program and the Windows program and what we've kind of experimented with. So this starts being kind of enlightening. You can see that there's a poke command that actually can just like write into any 16-bit offset, which is kind of scary. But so we have these primitives for reading and writing or parameter space that are actually pretty useful. So some stuff that we knew about that we can verify. We can find some new stuff, like this is how we found the calibration command, which isn't sophisticated. It's just storing 2 different reference angles, but this was the biggest hint as to how the calibration is supposed to work. You end up calling this with 2 different parameters, holding it in 2 different angles, and then it stores those. This is the command that attaches the PC, which is pretty relevant to our interests. And in fact, all it does is it checks to see if the flag is 1, which is the only value it cares about. And assuming the flag is 1, it just stores this value, this thing I've been calling main flag PC attached. All we do is store a byte to that. So yeah, we could certainly just move this, like set this as a default somewhere, and that would make the firmware a little easier to use. There's some other code that deals with this in the main, like before the main loop in main. I think that's dealing with the timeout and also with propagating this to the next microcontroller. So I think we might look at that code and see how to modify it so that it just sets this to 1 and then propagates it instead of waiting for it to be set. And then that might be a good way of making a very minimal patch to get what we want. So this is kind of interesting, but we're not seeing, like, a few things are notably missing from this. I'm not seeing command 1, which is what would normally handle joystick commands. And the reason I know about command 1 was from earlier in connecting a logic analyzer between the first two microcontrollers. Command 1 is what we saw the pulse width modulation inputs turning into as they turned into serial commands. So that's a pretty strong indicator that that's the joystick. So no joystick input here. But if we look at, so let's look at another microcontroller. This is MCU2. This is the one that had the most complicated firmware because this seems to also have some things that are, I mean, all of the microcontrollers seem to have some unique aspects to them, so you can't get the whole picture just from reversing one of the firmwares. But MCU2 seems to have the largest set of additions. And this also has a bunch of parameters that are only for this micro. So let's go to the corresponding serial loop in here. So if we just follow the same path, this is what I did earlier. I found the interrupt vector table, then the relevant serial. So in this case, actually, you might notice there is no handler for serial port 3. So this one, I think, speaks to the IMU via I2C, which would show up elsewhere. And so there is no downstream serial port at all. That's just like not enabled at compile time. But same story here. If you follow the serial 1 ISR, you follow it to the FIFO. Let's give ourselves some more screen space here too. So you follow it to the FIFO. I can see I annotated a little bit of the structure of the command FIFO here. And this poll function, and the read handler. So now we're getting into something that looks a little bit different. This is the same initial state machine, just taking apart the packet header and receiving the packets into a buffer. I haven't checked, but this probably has a buffer overflow opportunity in it. I think the buffer is only 128 bytes long, but there are buffer overflows elsewhere that are probably more powerful if you need that sort of thing, which we don't. Well, we might if we wanted to extract the bootloader, but I don't think we need to. I don't really want to do that unless we need to. So this one has a lot of the same stuff, but if we find state 7, this time there's a separate function handling the packets. So there's the graph. Another big ol' switch statement. So now you've got a bunch of new commands. So these are all the commands that the last microcontroller knows about, which I would expect this to be the largest set of commands, since this microcontroller is the one with some special features. So you can already see some old friends that I haven't annotated. Like this is the one that is the PC saying hello. Oops, and that's my keyboard dropping a key up. Here's a new one, 48. Something about changing joystick modes? That could be interesting. I wonder if this has to do with... So I haven't looked closely at how the joystick... Oh, the gimbal has just drifted against its end stop. I should fix that. See that? So I will need something to roughly keep it at the same heading. Oh, my joystick powered off too. Because that might have just been entirely due to gyro drift. I wonder if I could stabilize it with optical flow. Because, I mean, I was imagining that the higher level parts of this control loop would probably be visual in nature. It would be really cool if I could stabilize it around a particular point and then have a way of indicating regions of the screen to stabilize around in Twitch or something. Or maybe just have it based on a face detector. yeah, that's something to watch out for. Oh, Robert's saying, yeah, you can already patch code. You don't need a buffer overflow. Yes, I could just patch the code with a flash boot ROM dumper. That's just one of those things where, like, I don't want to dump the boot ROM unless I need to, and, like, I don't think I have any reason to. Like, it's only one of those things that would help people trying to clone this, which I would not want to help. Like, I don't want to eat into these folks' profits. Like, they're making a really nice product, but I do want to understand how to get the most out of it. There's just a tiny bit of magnetic sensor, or like drift even just apparent from looking at the magnetic sensor. You wouldn't want to necessarily like stabilize too much around that particular number. I don't know. It's like there are different effects that you want at different time scales here. At a really small time scale, you actually want to just disregard that because you want this to kind of float. But then at a longer time scale, you actually do want it to stay relatively constant. Anyway, at least we can tell which direction the gyro drifts in. That might change with temperature, though. So yeah, new commands. Command this 48. What is that in hex? That seems like a round number in hex. $30. This is command 30, unknown. That's interesting. You can tell it's doing something about this parameter that I've been calling joystick pitch mode, which I don't really know what this does. This changes how the angles are translated into pitch adjustments. So this might have something to do with orientation. But anyway, you can kind of read across here all the switch statement jump targets, and we can see how many of these are interesting. There's the calibrate from before. Command A. Yeah, some things that we kind of expected would exist but hadn't actually seen yet, there are handlers for in here. Same poke command with the 16-bit reach. So the one we're interested in is the joystick command here. Where's that? This might be easier not in graph mode. Here it is. It's like right after the jump table. So command 1 joystick. Yeah, let's maybe read this not in graph mode. So starting there, just the overall structure of this. So this is also maybe a little easier to chunk out. Like, actually, it would be really nice if there was a way to tell IDA, like, this is an inline function, please extract it. I'm pretty sure I can do that, actually, since this is... it just might end up kind of tearing up the rest of the function. Can I undefine this region? Which will, I think if I undefine this region, the rest of this turns into a function chunk associated with serial 1 handle packet, and then I can just define this as a separate procedure. Whoops. Oh, let's not lose my place. So this stuff down here should still be part of that. Can I define a procedure here now? No. Can I set this as the end of the function. Like, I've done this before in IDA where I have something which I know, as far as the compiler is concerned, is just one function, but then I carve it up into multiple functions to make it a little easier to deal with. Did I do that? I don't think I can do that. I think that it's like all the function prologue, epilogue detection stuff is just not going to be happy if I try to do that. Let's reset the function end. Oh, did that not actually reset the function end? I thought I did. Maybe I'm just failing to use this correctly. So I hit E. Does that not work because I'm in a data table? Ah, maybe that's the problem. So I think I just gave myself a tiny, tiny stub of a function here. Then I can separate out the individual cases into sort of function-like things. This is still a function chunk. I don't know of an easy way to detach things from function chunks. Like, I think you'd have to write a little chunk of IDC script or IDA Python or something. At least to do much of it. That's a mess. I don't think that's what I wanted. Okay, maybe let's just put this back. Fine, fine. Back to this approach. Back to this monstrosity. So anyway, this chunk from there to, where's our next command? Command 3. So a lot of these commands are pretty simple, but the joystick command actually has a bunch of parts to it. So let's take a closer look at that. These are laid out nicely in memory. The graph layout engine in IDA just makes it look like more of a mess than it actually is. Anyway, I don't have to do all of those right now. So the joystick code is from there down to right above command 3 motor off. So I'm interested first in looking at what happens to the payload. So as we understand it, this packet is made out of 3 half words, so 3 signed 16-bit ints and 1 byte at the end. And as far as I know, the first one is pitch, and then the next 2 are yaw related. So that's kind of what I've been documenting here. This is the last of those 3. So I'm storing it in this field. This is extracting a half word from the payload and storing it into this just variable. And like this isn't in param space. This is just elsewhere in RAM. And then this is the byte, that mode byte at the end. So this is the one that I don't really understand, but we've seen it do a couple things. In the communication between the first 2 micros, we've seen it be 0 sometimes, but it's usually 1. And I've been able to get the micro to respond in kind of a twitchy way to this packet if I set it to 8. So in fact, this right here is extracting that bit that we're setting when this is 8. So So right here, R2 is bit 3 of that joystick mode byte. So we're XORing it with this. So we're checking to see if it's different from this flag. Oh, which one is BPL? I need a cheat sheet for all these branches. Branch if positive or 0. So that's going to be looking at the most significant bit as we left shift this Boolean up in there. So this is like stuff the compiler generates when you do Boolean math in C. So I think what this is doing is checking whether that bit 3 is different from what's already stored in joystick mode in this variable here. That's interesting. So maybe that bit indicates what this packet is effective for, and maybe I have to change this param6 to the other value before the packets without bit 3 set are going to do what I want. What do we know about param66 right now? Because that could be relevant. I don't think we've seen it much. Yeah, I've got some notes about it here, but it doesn't seem to do much. What is it set to right now? Let's just give ourselves a web UI for param66 so we can adjust it. Oh, it's like right after follow rate, so maybe it's also follow related. It is interesting though that it would be being read like right in the joystick handler. It seems to be another Boolean. So I'm going to leave this blank since we don't know what this is yet. 66. Cool. And the max should be probably 1, although I might set it to 10 again just so that I can experiment with larger values to see what happens. So this should be still running. Cool. Got our little dashboard. And let's turn on the camera so we can see what's going on. Don't stop automatically. Robert saying that they find IDA doesn't like inliner tail calls very much. I mean, you can definitely carve stuff up. It's just sometimes kind of annoying, and I would have more automation for this in Python if I did this more often, but as it is right now, I'd like to do some little things here and there, but the VM I'm using right now has a really, really broken Python installation, and the other one is in the middle of updates. So, not in the cards right this moment. Alright, so this is back to being useful. Okay. That's interesting. It looks like it's getting set back to 0, but when I change this, there's a little tick in the gimbal. So we might be on the right track, but there might be a different way we have to set this. That little tick might indicate that a mode has changed or that it's temporarily accepting our joystick packets and doing something with them. That's interesting. Let's see where else that one goes. Let's make sure we save this often. Joystick. Yeah, so what is writing to this? We know somebody's writing to this now. Right here in main? This is just going to be initializing it though, right? Yeah. So it is initialized to 0 at every boot up. There might also just be instances of this that we haven't caught. Because for it to show up in a search like this, IDA needs to know about the base address of these stores. So for example, if I just change this back to a number, see, you're just seeing this offset. We have to know that R6 is a pointer to the first parameter in this case. So let's actually just look for instances of this, that's CC, and then we can add the offset ourselves, like that. So we'll find all occurrences of this and sort them, and 2 candidates. There's one here in serial 1 handle packet and one here in this subroutine. Both of those seem relevant, potentially. And another load. So we can go through and annotate all of these if we want. So we expect to find that R0 is a pointer into parameter space. Maybe this is not, maybe this is a red herring. This might be unrelated. Okay, that's not relevant. What about this one? Yeah, this one, all these are in param space. So we can go through and, anything that accesses R0 here, we can set it as an offset from parameter 0 in IDA, and then it'll actually give us cross-references where we need them. So then there's one here in the timer. That one's already annotated. I think it's just down to this one. So I think this one's also unrelated. This just looks like math. This is a calculation based on what now? Yeah, this is just some kind of table store. So that's not important either. So in that case, I think we've pretty much localized our thing. Our parameter table so far. We can see what is cross-referencing to what. Param66 joystick mode. So there's the default value. I think this must be what's setting it right here. Where is this? So this is actually a state flag that's used inside here. This is maybe mode is not accurate. This might be doing some kind of checking to see if it's changed and then setting it if so. Let's see where this goes. Oh, that's from bit 3. Okay, maybe this is the same as bit 3 then. We're just setting this directly versus setting it from the packet. So let's rename this. Joystick last byte bit 3. That's pretty generic. And so where else does this go? Is this a mode toggle? It is being used in the motion control loop here. Where does this happen? So timer 4. This is doing a bunch of the slower motion control in the gimbal. So a lot of this is going to, be doing different things in different modes. Some of these branches you're seeing are like piecewise functions. Some of them are like min, max, or absolute value implementations that are inlined. You can see some places where it's accessing the joystick yaw, for example. That's interesting. Anyway, this is the section, this is the actual follow loop with its 2 implementations. So you can see here, this is the follow enable that we've been using. If you look at the similar code on the first MCU, then this just kind of acts as an on-off switch. But on this MCU, we're selecting between 2 different algorithms. So I think I got this logic backwards. I think this is with follow enabled. Does that make sense? This is branch if less than 1, which seems to be follow disabled. The behavior that we were seeing from this axis was, with follow disabled, it's always pointing at the horizon. With follow enabled, then it was tracking movements. If the mode where we're always pointing at the horizon is the one where the joystick is being respected, then that's good news, because that's closer to what we want this doing. I had just gotten myself confused about which one of these was which, but I think, I'm pretty sure this label's right. This is 1 when the follow is enabled. Comparing it against 1. Branch if it's less than 1. This is follow disabled. So if this is, and this is reading the joystick inputs, so I think that's what we want. So let's reflect that in our controller. Yeah, this is just change it back from enable to disable. And I don't think the follow loop has any effect for the roll axis, but if it did, we would want it on. So let's keep the roll stabilized in whatever. I don't think it even looks at that, but might as well set that to 1. So, okay, what else do we have here? So this is the mode where follow is disabled, and we expect it to be horizon plus joystick. This is the mode where follow is enabled, and I think this must be a local follow state. Or accumulator, rather. I think this is where it actually looks at the distance and then makes different movements. I think this is basically follow hysteresis. You can even see I've already labeled this as hysteresis with a dead zone. So that also matches what we've seen so far. With following on, there's that hysteresis behavior, which is this code right here. With follow off, it just locks in exactly, which matches more what we're seeing on this side of the equation. So then this seems to be good. Maybe we don't have to patch it. If we can make this code behave, then we don't have to patch it. We could if we wanted to. I want to have a good understanding of any code I patch because it seems easy to break things in subtle ways with this code. Let's keep that in the middle. Andy says, hi, I always love opening the stream to Ida. Yeah, me too. It's nice, nice doing some reversing online. What? Oh, geez, how did I do that?
Everyday man turn up to the max.
I just pressed something that started Spotify.
Went to the hills, trying to kick back.
I really don't need more trouble from the copyright robots. Alright. So this little chunk of code is the follow loop that I think we want to be using here, unless we just want to patch the whole thing out. The end result of this thing ends up being something in param3. Where can we find that? Yeah, control rate. So this is the end result. This is the same thing that we've been setting manually on the yaw axis with the follow loop disabled. But this you can see in all of the different implementations here. So these are all the ways out with the follow loop disabled. And these are all the ways out with the follow loop enabled. They all set the control rate, so there's no getting around that. You can't set this manually without patching the firmware. All routes lead through here. But I think this half of it might actually be close to what we want. So this stuff down here, I think, is related to clamping the extremes of the motion. Maybe I need to relay this out. So, yeah, I hope I don't get another copyright bot breathing down my throat because of my always having a keyboard map to Spotify somehow. Anyway, so this stuff here is, I think, just kind of a piecewise function that breaks this up into different ranges. Peter says it might be good to restart the stream. I guess we could do that. I don't know why that would help. Since YouTube would glue it back together anyway. If I restart the stream, YouTube doesn't set, I think I'd have to be offline for some duration of time for it not to glue those back together. And whatever, I don't really care. I'm not doing this for the stream archives, I'm doing this for the edited videos and the cat cam. But I do get annoyed that this is a thing. Anyway, these rates, I think, actually are pretty small numbers. I think this is some dead zone stuff again. Anyway, this comes from R1. This is some fixed point division. This is like an idle state where it's locking onto a 0 rate. Can I not move this side to side anymore? Oh, that's what happens when the joystick goes to sleep. Yeah, I'm not going to go through this entirely, but this is just like a piecewise function, I think, that they're using to condition the speed as it comes out of this loop. And that all comes from one of these places. So we have these two ways of doing things. Yeah, this is that param68 joystick pitch mode that I was looking at earlier. Well, we saw it before. I haven't really looked into detail here, but it seems to select between these two different algorithms, which seem to be pretty similar. Like this chunk is the same. This is just another little piecewise clamping function. This seems to be taking the joystick from the joystick control from the packet and converting it from like microseconds into something else. So it's subtracting the center location, scaling it by like 18,000 or something like that. And then based on param68, we go to one of these two places. Oh, Nick said maybe a big red e-stop button set up to cut the stream audio. So I did actually reach for the button. I just forgot that the one that killed the audio on the speakers wouldn't actually kill that on the streams. The whole reason the audio even comes out is like me mixing up my buttons. Like if I always knew what every button did and never pushed any buttons accidentally, we wouldn't have this problem. And yeah, I just don't need more things to worry about right now. So on this side, we just take the joystick angle minus the gyro angle, which seems simple and elegant and exactly what we want. And I think this is the same thing, but with some kind of offset or wraparound or something. This is that same subtraction, but then we add this, which is a big negative number. What is this? I don't know if there's a good way to get IDA to seamlessly handle negative or like otherwise signed numbers. Yeah, that's negative 18,000. I think this is just handling wraparound to like invert the polarity. That's just subtracting that. This is joystick angle minus the gyro angle. Same polarity here. This does drift when you just leave it alone. I will have to counteract that on my own without its follow loop running. I mean, I could run its follow loop if I had an offset to it, but it seems like I'd rather just write my own. Yeah, I think this is just doing a wraparound. Anyway, this looks like what I want. Why isn't this working? So, I think I want param68 set to 0, but it shouldn't matter that much. I don't... let's set this to joystick pitch offset flag. Joystick pitch offset flag seems like what it does. So we want the follow loop disabled. This is the field. So R0 is the joystick input that we are dealing with. It's clamped to 9,000, which is cool. And field 0 in the packet, which is what we're doing. Let's just try this again and see what we get. See if we can identify where the problem is. Yeah, I really can't be bothered to get caught up in YouTube drama. That's just not where I want to put energy. Okay. Our command is going out. Target 2, command 1. I still don't know for sure that this is actually making it to target 2, but I'm pretty sure it is based on how it was twitching when I would send 8 before. I don't entirely know what this last byte is, but I'm going to send 1 there for the moment. And we definitely want the follow loop off. You know, maybe it's starting up in the same mode where I mean, so normally the joystick has a few different kind of user accessible modes where either the gimbal is totally locked into forward mode, or there's a pitch offset, or there's a pitch offset plus yaw speed control, kind of like what I've got now. And so maybe the joystick is still in that kind of totally locked mode where it's just not responding to my fake joystick packets. That's kind of what it looks like it's doing, but isn't it? I just don't see anything in the code to suggest that. I mean, I could just patch out this entire loop, but yeah, and then I would have to calculate control rate. I think all this is doing is trying to hold the gyro angle at some reference. What does param 9 look like when this is operating? Is that like centered around 0? That's minus 30, that's like 17,000. Could use a numerical readout of these things, but yeah, I just like forced it away from center, and if you look at the 9, I think that's 0-ish. And I think the yaw axis just works totally different here because it doesn't have the same, like it doesn't have like a baseline. But the other two axes it calibrates using gravity. So that's cool. I could totally just redo this and have my own loop. Just patch out this code. So that's totally on the table. If I made a binary patch to this firmware to just remove everything from like basically just have this jump directly to this block right here. So then I could calculate this param3 control rate myself based on the gyro angle. That might be really nice. That would give me the same control strategy for yaw and pitch, which would be really nice. So that's one strategy. The other strategy would be to continue to try to make this code branch do what I want. I don't totally understand why this is not already working clearly, and that is kind of compelling because there's something I don't understand going on here, and it would be nice to know how to fix that. what this is. Restoring something to this field. Maybe that's a flag indicating like how we got there, or what to do with the result somehow. This is actually where it integrates the differences in the current heading. We definitely don't want to move this off the microcontroller because that would make smoothness a lot less, but it's useful to know how this works, so that's kind of a neat piece of code to have handy. So we could patch this. But this seems very close to working. So, I mean, the fact that it's locked onto the horizon reference means that it's in this code path, because this is the code path that actually follows the horizon. So we're getting here. We just must not have the ability to set R0 to something significant. So this is just clamping. It's always going to come up through here. I don't see any way of this field not taking effect. So is there any way that maybe we're not setting that? So that gets stored in this packet handler. Okay, this is where we're looking to go, this line right here. There are some ways to get out beforehand, huh? Right. I wonder if it's just going to ignore this when the PC is attached. So that's not an out, that's just... But this is the first actual... This is probably where we're falling out. This is just ignoring joystick commands when the PC is attached. That's sad. So I guess we're patching this. Okay, well, the first step to patching this is having our own firmware packer and update tool. So that's the next subtask that we need to visit. I mean, if I really need to edit YouTube archives, I guess I could do that. I would just really prefer not to spend what little editing time I have on stream archives when I could be doing something else with the video, you know? Okay, let's look at the firmware update process and maybe try to replicate that. So we have traces from the update. Oh, I did not actually... I have the sigrok file for this, but I hadn't actually unpacked this yet into a text trace. Let's do that. Sigrok CLI. Yeah, so that's the raw trace, but we should do some decoding here. So we want a protocol decoder for, oh geez, this was a complicated command line. Do I already have this in my history? Oh, can I cheat? Nope, that's fine. So, protocol decoder, I think we want UART. Is that what this is called? How far does that get us? Is it UART? Oh, and these need colons. Alright, there's our serial. And then we want to stack another decoder, which will be our FY Gimbal protocol decoder. And then I actually only want the annotations from that. So here's our data. You can see the firmware chunks rolling in. Let's store this in a text file. It's Friday, isn't it? How's everyone's Friday doing? Yeah, it's totally Friday. Ah, yes. This one is a little slow. Let's take a look at what we have so far. Oh, so this is actually all different from what we've seen so far, because now we're talking to the bootloader instead of the Gimbal firmware. So these are all AA55 commands. Like all of it. So that supports the theory that the two different packet types are actually two completely different code bases. So this one came from the Gimbal. This was it announcing the current firmware version. So the bootloader must be reading this number out of flash somewhere. I wonder if that's coming out of the default parameter block for that micro. We're also only seeing this from target 0, which is the current, like the micro that's attached most immediately to the PC. So that micro is saying, hello, I'm a bootloader. And then the PC is saying, oh, you're a bootloader. Wait, stop booting. We have stuff for you to do. So that's the bootloader command 1. And then it just starts sending blocks. There's no like, please prepare a buffer for this or something. It's just, hello, have a block. So command 2 seems to just be have a block of encrypted data. This starts off with a number, which is most likely 16-bit. And then something else, so some kind of 4-byte header it looks like, starting with a block number. And there's a, yeah, this is probably a 2-byte block number because we are getting these confirmations back. And that's command 3. So it looks like 2 is program block and 3 is block confirmed, or like block program done or something. Is this done yet? Yes. Okay, so here we're just seeing a bunch of blocks being written to the first microcontroller. This will be repetitive. One question is it specifically avoiding sending the block that contains the parameters? So if we look at any of these plain text firmware images, near the end we see a block of parameters at this kind of conspicuous location. So if we convert this back into a block number, block 96, which is 60 in hex. Well, it is writing to that block. That seems to be the last block that it writes. And I don't see anything special about this command, so maybe they don't do anything special to save the parameters and the bootloader is responsible for that part. So command 3, command 2, etc. Then this is the acknowledgement from that last block we've written. Then there's a command 7 with a reply of command 8. I'm guessing this would be the way you finish the operation. This might be how you talk to the next micro. But, I mean, they might also be doing something else. Let's see where this goes. So command 7 with a 1, then 8. Because this doesn't seem to be exiting the bootloader, so it wouldn't be like an exit bootloader. And I don't think that they're writing this to a separate area. I think this is writing right on top of the active flash. So maybe all this does is switch to talking to a different micro. So then we have more blocks, and we could check to see if this matches the second firmware image if we wanted to. Same thing, ending in block 60. Then we have 7. So again with parameter 1, so that doesn't seem to be what you would do if you wanted to talk to a different micro. Unless it's just always like, maybe what this command does is it puts that micro into a pass-through mode, and everything after the 8 is then communication with the next one in the chain. So maybe you just do that every time you want to like knock down to the next one. Oh, Alex is asking if I can't cast to Twitch again. No reason I can't. I've been thinking about doing that again. I've got an account on Twitch, and I might just start casting on the creative channel, which could be nice. I think before with Senrio, I was doing it more because, you know, I wanted to have a separate thing for them than because I wanted to intrinsically have two things to manage, but it is nice having a backup thing. So I've been also casting to Beam.pro so far, but I haven't really been trying to like build up the channel much. I've just been using it as kind of a backup. So is this going to be the third one? This appears to be the end. Oh yeah, it's done right after writing that block. So that seems to be, I think that validates my assumption that commands 2 and 3, like this is the entire firmware update cycle, and command 7 is like a daisy chain command. So I think that's what we're dealing with. I suspect what we're going to see in the bootloader is, I bet when we respond to this command by sending, you know, as a command 1 response, I bet this gets propagated along the whole chain. So each one sends the command 1 to the next micro and the next micro, and then most of this is just dealing with local micro. This target seems to always be 0 in this protocol. Maybe that's not even a real field in this protocol. Maybe the commands are actually 16-bit this time. I don't know. But then between micros, we have this command 7, which seems to be a daisy chain. So the device doesn't even see the CRC. So like if we're making our own firmware update tool, we don't really have to check it, but we know how to do it, so we might as well. Let's make a firmware updater. So we want pack and pack and flash seem like good tools to have. So we've got this unpacker. Let's have a packer also. You're not going to give me folders? Oh, I just made this on the local machine. I want to do this on the Raspberry. Whoops. Fine. And I guess let's copy that image. Okay, so that's the firmware image that we started with. Let's go back to the Raspberry. Gimbal is powered off right now. Okay, so we can run unpack. Oh, we need PyCrypto. I want pack to do the opposite of unpack. Let's also maybe get unpack to... I should really have one command line utility to do both of these, but I'm gonna potentially be lazy. Let's have this test the CRC at least. And we were saying the CRC covers everything past the... Oh, I'm gonna have to cut this up differently. Let's read it all in first. This will be the first 8 bytes. Let's just do it that way. Can't run that yet, but we want, so the CRC we want to use actually happens to be the same one that's in bin ASCII for doing the old like Mac HQX format. So yeah, this one with an initial value of FFFF. I think it was everything after that, but we can adjust that easily if it isn't. You still working on that little pie? Let's just call this assembled right now. Oh, great idea from Michael. It would be nice to confirm whether the index of the 3 images in the file matches the target number in the serial protocol. Yeah, no, that would be great to confirm. I guess I was about to make that assumption, which could have been bad if it was wrong. Let's check that out. So that was in my other source tree. Oh. Yay, I think we're good. Let's just open that up in another editor. Okay, let's find these initial blocks. So we have an EO26, blah, blah, blah. That is the first image being sent first. Okay, here's the beginning of the second image. Exactly where we'd expect it. I think we're fine. Let's find the next one. Yep. Cool, so we have those 3 in order with a daisy chain command. Actually, I kind of wanted that thing that I just closed. Not that one. Fine. Let's just update this source tree so I have it here too. There we go. So unpack. Oh, CRC seems fine. I just need to fix this other bug. Something like that. Oh no, tabs. How did I get tabs in this file? Cool. Okay, I think that's as full-featured as it needs to be for an unpacker. Let's just have the opposite of this. Okay, so we've got firmwares. Sure. You're talking about three 16-bit numbers, right? Yeah. Just some coding, you know, putting numbers and symbols together on a page. Let's see if we can assemble a firmware in the same format. Oh, ha! I meant to make that integer division. So we have a firmware assembled. It's the same length as the official one, which is a good sign. Let's have these side by side. Actually, let's just diff them. They should actually be the same because I haven't patched it yet. Cool. So we can now assemble the firmware image, which is not that surprising because it's a really simple format, but great. Now we just need a flasher tool. I kind of want to use this module that's up in a higher level directory, which is slightly inconvenient. Let's maybe put the flasher up there and leave this to be stuff that's just dealing with the files and not the protocol. Let's just call that fyflash in the previous directory. Okay. So then this fyflash thing, this is going to be using kind of the lower level interface. So we aren't probably going to be using this Gimbal port class that we've been using for most of the Python code. So here in fy serial land, we have some low-level receiver and transmitters that might still be useful. But a lot of this stuff is not applicable when we were talking to the bootloader, I think. I thought I had a program here that was already using the low-level interface that we could use as a starting point. Oh yeah, raw packet tool. So yeah, this is just making a packet receiver by itself and then sending packets. You don't even need the packet transmitter as a separate thread unless you want that to be non-blocking. So yeah, this is a good starting point for what we're doing right now. Let's have this and fyflash. Something like that. Okay, let's be liberal with the print statements here. Oh, we do still kind of want this transactional back and forth command style, but since this is just the bootloader, I don't know how much of this I want to actually add to the higher level classes. Yeah, I mean, this is the packet I'm dealing with. I don't really want to mess with this because it's not obvious how the bootloader would operate with the rest of this class, so I think I'm going to make this separate for the moment. So we're looking for this packet. I don't even know if I'm going to bother with timeouts here. So yeah, just use that nested loop thing to do what I want. Okay, and now we need to respond. So we're still way up here at the beginning. We just got this packet and handled it. Now we need to send this packet, which is a command 1, target 0, no payload. Alright, that's our hello packet response. So, I mean, and then this just like launches right into Flash without even getting any more confirmation, which is a little weird. Let's maybe skip that step first and see if we can do the microcontroller daisy chain thing. Since if that works the way I'm imagining it does, then we'll be able to run this twice to hop from the first microcontroller to the second to the third, and then it'll just stop working because nobody will be responding. So that's the sequence right here. So wait response. Let's just generalize this very slightly. Most of this is just encoding the packet, and I just wanted to have a function for it. Mostly so I can add some debugging for this. So 7 and 8. Let's just see if we can do this a few times. I'm going to expect it to fail on the third time. So the first two should work. The third one I expect to fail. I think this is defaulting to tabs. Okay, and it wants a file name, which is cool. I can give it a file. Okay, let's see if I can stick around in the bootloader. Powering on the gimbal. Let's fix that. Oh. Packet. Oh. Did that work? Let's see what happened. So we connected, oops. Connected, and that's our reply. Then here's go to the next micro. So we got 1 response, 2 response, 3 response. So the third micro responded to this command, but now we're just talking to nothing. So, okay. That's one way it could have been implemented. I could have also imagined the third micro not having a response to this command. But it might just be that the bootloader's the same on each of them, and this is just talking to something that isn't connected to anybody. I see no reason why they couldn't make the bootloader the same on all the micros, so that's kind of what I would expect for simplicity. So that seems fine. Let's also have a really simple wrapper around the firmware file here. And there are some other things that we could deal with, like 2-axis versus 3-axis firmwares, but I think right now I just want this to check the CRC and give us sizes. Let's just yank the CRC code from here. Okay, so that'll be the same. And then oh, might as well just parse this all out. Oh, I need a way to sum all of the previous elements in this. Is that how this works, or yeah? So it'll be the total of all the previous MCUs plus this index. I kind of want to test that separately, like just make sure that I can grab a block and then it matches the one in the protocol before I send anything to the micro. So, and I don't need these. Let's make sure we can read the firmware file. Oh. Still not entirely used to the print as a function, but it's nice. Okay, so that should be the first block. EO26A, blah blah blah, ending in E3D2. Cool. Let's also spot check a few others. Like the last block of that micro, maybe also the first block of the last micro. C8, A4. Oh yeah, this is the parameter block, which is going to have a lot of similarities. That's the version we're looking at. Yeah, that's the first, second, third. First ends in 7B210. Cool. That checks out. Let's try that same thing on the last micro. Just want to spot check this because if I program the wrong thing, I don't know if I'll be able to recover. I'm not sure if the bootloader is designed that way. I mean, I'm sure there are some things I could do, just like by blowing away the bootloader or grabbing it from a different micro, but I prefer not to have to open those cans of worms if I don't need to. This looks fine. Yep, that's the one from the last micro. Okay, I think my firmware file reader is working. So this is so simple. All I have to do is say hello, send each block, wait for the corresponding confirmation, and in between micros send the little daisy chain command that switches to the next micro. Command 2. I don't know if the second set of 4 bytes does anything. I'm not sure if this is a this is like a reserved field or whether this is actually just an 8 or a 4-byte integer just for the heck of it. Oh yeah. So just catching up on chat slightly, Robert says you can probably use the Windows blob to do the actual update. I know I could, I just don't want to physically have to plug this into a machine that can run a Windows VM because this is going to be attached to a Raspberry Pi. So it seemed like a useful thing to have my own updater that I could run on the computer that's actually connected to this. Yeah, and then Michael also mentions that I could probably have it not flash everything, which also seems like a useful optimization. Which is nice. I mean, a lot of updaters, you wouldn't have that flexibility. So yeah, maybe I could have a command line option for just, like first block, last block or something. I'm going to assume this is a short integer and then reserved. then the response should be a 2-byte packet that has the same number we sent. So it's definitely worth confirming this. Something like that. So it's harmless but unnecessary, I think, to call next microcontroller at the end. It's basically just cutting off our communication channel, but it seems like it'll succeed still. And then up here, and then we're just getting firmware.block. Okay, well, we could just try this and hope for the best. It parses. I mean, it would be nice to have more of an experiment to do than just like run it and expect nothing to change, but control experiments are good. It would be nice if there's something a little bit less risky to try. We could try just setting the data block. Let's add some parameters for first and last block. Oh, how do I tell if this is an integer? Type equals int is what I want. I think I want that hexint function. I think I want these to be in hex. I mean, I could make them in arbitrary base. I think I do want this to be hex. That's one way to do it. So if we look at the help, we can see first block, num blocks. Let's try just setting the last block. Which is 60, right? So that would be this file, then first block 60, num blocks 1. Oh yeah, Michael's suggesting another test with a fake response to verify before flashing. I think maybe the thing to do next is to run this without the gimbal powered on, but just comment out the parts where it's waiting for a response, and then see how it responds. Some paranoia is justified here, because a small error in this could easily brick the gimbal in a way that I then have to go on another saga to try to unbrick. So let's just skip this with a return. Gimbal is powered off. Let's just see what this does. I'm gonna find all of our little syntax errors. Oh, that was actually just... Let's return a bogus packet here. Precedence. I was trying to divide the string. Okay, let's see what it's doing. So here's a write to the block we expect. This exact packet should match one of the things that we see in the actual firmware app, so let's see if we can find that correspondence. This is the wrong instance. It should be this one. Assuming this encodes correctly, that's fine. We've already had a good amount of testing for the packet encoder decoder at this point. Alright then, I'm gonna try this. I think I'm happy with it at this point. So if we take that out, now we're back to this point. Okay, let's try actually powering on the gimbal, and this will just reflash the last block where the parameters are. That looks like it did a thing. Yeah, we just programmed that. Let's see if the gimbal is still alive. Oh, let's try that again. I panicked and unplugged the power. Yay! So the code that saves and restores the calibration must exist on the device side, because if it just blindly wrote this to every flash block, this would have blown away the calibration again. So next stream, restoring the gimbal's bootloader. Yeah, yeah. Well, so far that's fine. Let's see if we can flash the entire firmware. So this is without the num blocks and first block arguments. We're just flashing the stock rocker position mode firmware. I guess I could try flashing an older version of the firmware, but I think I'd rather try patching it. I could try setting the version code myself to see if I can patch the version easily. I think the first patch I'm going to make is though just turning off the yaw follow loop. Anyway, enough procrastinating. Let's brick this thing. It'd be nice to have an indication of which microcontroller I'm currently programming. Here's programming all the blocks that are the same because they're empty. Second micro. Most of this is actually just waiting for that response, so this is definitely throttled on the microcontroller doing flash blocks or block erases and stuff. Oh, that's also a good question, or a good thing or a good suggestion from MakeOMK, who says, "You're sure it's writing to the flash block with the actual parameters, not just the defaults?" And actually, I'm not. It's quite possible that it saves the actual parameters somewhere different. I haven't really looked at the code that does the saving to flash in detail. Well, I think we just wrote it. Let's see if our Gimbal's bricked. I'm just going to power cycle it with nothing else running. It's still alive. Great. That's a good sign. And this should be in follow mode again, because it's just running normally. Maybe the first patch to make is something that keeps it in serial mode, because that's seeming super useful now. So what do I want to do these patches in? I think I just want a little Python program that pokes stuff fairly dangerously into the MCU files at this point. Let's maybe commit what we have, since this seems to be a good chunk of stuff that works. I forget exactly what this was. I think I was just fixing some bugs in the parameter UI in the socket server. And I already checked those in, right? Yeah. Cool. I think we're ready to hack around in the firmware image. So, do we do the follow loop first, or keep it in serial mode first? I mean, the follow loop seems like an easy first thing to change, because I've already reverse engineered exactly what to do there. I just need to assemble the new code. So we want to go to the timer for loop in microcontroller 2, which is the pitch microcontroller. And I just want to disable its follow loop so that I can implement it on my own. So this is the code we're replacing. Normally it's calculating a pitch movement speed, which gets written to this control rate vector. And as you can see, there are a bunch of ways we can end up there. There's no way around it though, and I would like to write that myself, since this code is not being super cooperative, and calculating that value on my own seems like a really nice clean interface boundary between the two sides of the gimbal, basically. The really low level side and then the high level heading tracking. So I think I just want this to be a jump. This is actually something that IDA is not super good at, and there's probably a different tool that can do this part a little better. So I want the jump target. This is often when having a way to write stuff down is helpful. This is in the MCU1, or sorry, MCU2 follow loop. So my jump destination will be 800B416. This is the basic block I want to end up at. And the place I'm patching could be like anything in this basic block, really. This register is not important, right? Yeah. None of that is important, so I can just splat over this basic block, basically. 800B2BO. So if I had a tool that would just let me assemble a single instruction right on there, that would be the thing I do. I don't know if IDA has that mode. Let's see if it does. It's been a while since I've done this on ARM. I think it can only assemble when it's in debugging mode, which would require a target, I think. We could also calculate it manually. Here's a branch over here we could use for reference to remind ourselves how branches work in ARM. We could look at I mean, there are many ways to do this depending on how much you feel like sculpting the wheel by hand. Let's turn on line prefixes and opcode bytes. So now we can actually see the binary behind this. So as you can see, this is a really small branch. This may not work for the situation we're in right now. Oh, I feel like this is something I want to learn some new tool for, because I don't have a really good just like tiny ARM assembler type thing like that in my repertoire right now. I know about Capstone Engine. Is that x86 only? Not engineering. That's a disassembler. Is there like an ARM assembler in Python that I can use that's fun? Oh, MakeOMK is suggesting using Radar 2. That's a good idea. I don't have much experience with that, but this might be a good chance to learn a new trick. Do I have that installed on here? I don't think I have it on the Raspberry. Do I have it on here? Is it in Homebrew? Oh, Gimbal seems so happy. Yeah, I mean, if this is something I could do with like a little Radar 2 script, that would be nice. I mean, I can show you some of the solutions that I've had to this problem in the past. Like, I've definitely done this before on x86 just by writing terrible things with NASM and Python. Oh, this isn't it. This is something different. Yeah. Where is the code for this? There we go. Yeah. So like one of the ways that I've done this in the past that required a bunch of boilerplate, but I ended up really liking the end experience, was to have this little Python framework where, let's get to the good part. A lot of this is framework, but oh, I guess this is a really older version. I think I had a nicer version of this that I wrote for the DS port where we just were. Oh yeah, this is what I was looking for. So it'll do things like, this is basically just a hexadecimal pattern. So it'll look for these hex bytes, the underscores are wildcards, the colon is the insertion point that it ends up with, and then this ends up inserting a no-op right there. So this is like something where I didn't want to just include a copy of the binary, and I wanted to keep track of the kind of the trail of changes that I needed to make. So some of these just patched addresses with instructions, but then some of these used expressions like this to put in replacement code. And that's what I'd really like to do, something like that. So that seems like something that Radar 2 could help with. Cool. Let's see if I can get an example of how to use this to patch ARM binaries. Can I patch it on the command line even? That would be handy. Okay, so we can set the architecture, which is useful. Ooh, and the base address. Let's start collecting options in another window here. Yeah, because I mean, if I could just have a shell script that applies to patches using Radar 2, that might be exactly what I want at this point. So let's try ARM. I mean, is there like a sub-architecture I would need? Commands. Oh, RA patch files. That seems useful. What does that do? Oh, nice. Seek, print disassembly. Maybe let's just try interactively poking around in this binary before getting too carried away with command line flags. So let's see if we can just load this as an ARM at this offset. It's fine. Seek. Can we confirm what's at this address maybe? 800B2BO. And how do we disassemble? Is there built-in help? Is that a file offset in the prompt? So we can seek to address. Oh, and you can just type a hex address. That's handy. Okay, and I guess it doesn't default to hex, so that was an error, and that is actually how you seek. Okay, so you need the OX. And what is the disassemble command? Print disassembly. That doesn't seem right. I think this load address didn't quite do what I wanted it to do. Dash capital B. Oh, that was the block size. What? So this says base address for PIE binaries. This says block size. Neither of those are what I want. I mean, I don't have to give it the real load address. I could keep it all relative, but that would be nice. Robert says that they would have used bin utils to assemble this. I've done that too. I just want to learn a tool that's better for this. Oh, seeking before loading is maybe that the way to do this. The examples I was seeing so far shows it loading like an ELF file or something that has a base address built in. Is there maybe just like a load command I can issue? Oh, what is dash s? That was the seek address, right? But that doesn't affect before I do the load, does it? Let's see if it does. No. It's still loading it at 0. Oh, interesting. It looks like Mark found... Oh, it looks like MakoMK and Mark both found -m. I just didn't see that tiny text up there. Sorry. Where was that from, just for reference? Because I like to know how to find things. Is that not in the man page? Oh, there it is. It's not in the man page, but it's in the command line help. Great. And it seeked that address. That's fine. Okay, that's full ARM code. I want thumb code. So we were thinking maybe 16-bit mode, which seems a little weird. Because it's not really 16-bit. That is at least, so that's not code, but it's at least disassembling it as thumb code now. So can we get a disassembly of this address we care about? Yay. Yeah, that looks right. So we want to assemble and then write the file back out, I assume. Is there a way to turn on read-write mode from the command line? Because I could just do this on the R2 command line there, but what I really want is to have a reproducible script, so I kind of would rather do it that way. I guess I can just give this some commands. Or -I for a script. Sure. I don't know what extension to give an R2 script. Something like that. Let's try this. So I just want like an overall shell script that runs the individual patches and does the packing and unpacking. Yes, let's make that non-interactive. Oh, -W is open in write mode. Cool. Quiet mode, is that what we want? Maybe we don't want quiet mode, maybe we just want the script to have an exit at the end. Maybe -Q is what we want. Let's try that. Yeah, I think that's right. Okay, so we can take it apart, put it back together, no differences yet, which is great. But now we have a place to start putting some differences. Let's just keep a little placeholder for the ones we're not using yet. And an M2. Okay, so that address, I'm assuming these are comments. I don't actually know if those are comments. Can I suppress this warning? Maybe I don't care. Maybe I don't care. Ooh, so WX for writing hex. Is there a write assembly? Let's go back into this file interactively to poke around with it. Not in write mode for now. Did it save our seek address? That's interesting. Cool, and that's doesn't increment, it just sticks there. Cool, that's great. I think I want a smaller block size because that's enormous. Right. Write opcodes. How do I make my disassemblies tinier? Ah, B is the block size. Load, compare. So we're right here. 8, blah, 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 B, 20. Cool. You are here. Let's try doing an assembly right there. You can alter or modify an opcode. I think we just want WA. And this would be a branch to 800B416. And I think it's just telling us we can't write. I was assuming it would give me a temporary buffer, but maybe not. That's fine. I'll enable writes for this. Ooh. That is not the right kind of instruction. It looks like an ARM instruction instead of a thumb 2 instruction. Oh, that's really handy. What is this doing? There's just a little command line tool just to do the assembly. We're gonna get the same results there. That is weird. Oh, does it want BL for long branch? Yeah, so these are short branches, but there's a longer format of branch that, and this isn't even what I was seeing it assemble. What did it assemble? It assembled that. Okay, what was block size? B? Okay, block size. See, that's just writing 2 bytes. Maybe I'm just forgetting what this calls that opcode. Let's just pull out a thumb2 reference. Yeah, so I mean, it was generating the short version of both B and BL. We could just make this an indirect jump, that's fine. Geez, now how does the assembler here do literals? I don't think I need such a large jump, though. Let's see, so how big of a jump do I need? B2BO to B416. That's more than 256. So how would I usually encode that? This is not the encoding reference, this is just... Oh, Robert says try b.w for a wide branch. Is that how we have to encode this? Let's see what that does. So print disassembly. That's still just writing 2 bytes. What? This is just not assembling and disassembling correctly. doesn't look at all right. What happens if I restart this? I think it's getting the endianness wrong. So I just tried assembling. Do I have to tell this the endianness differently? So I tried copying this compare R0 to 1. So I assembled it at the beginning of the block, which should go right here. And so we can see it usually is represented by 2801. So we ended up with 2801 up here, but in the wrong byte order. Dash E. Huh. The arch and parser are different here. That seems weird. Oh, here it is, config.bigendian equals false, so that's not it. Am I hitting a bug with the ARM port of Radar 2? Like, would this be different if I ran this locally? Let's at least try to make a reproducible case for this, and then I'll try running it on the other computer. I think that should be the script I want. Let's also have a smaller block. Yeah. Let's see if I have any luck. Do I have R2 installed on this Mac? I do. Let's try it here too. What? Is it making fun of me for having an IDA key on this machine? I don't have an IDA home directory here. That is super weird. I have an IDA in a VM here. What is it doing? R2. Syntax error, error in error handling. Yeah, that doesn't seem like it's working very well. Oh, did I forget to tell this ARM? Oh, that could be a problem. Okay, so that is the incorrect result here. Let's run unpack again to get a fresh binary. Is that still not fresh? Oh, I was just catching up in chat reading Mark's comment, and then Robert explains what's going on with this. Yeah, I haven't synced to the right address, so I'm not seeing what I expected. Thank you. Oh. Is that, what debugger is that from? Is that WinDebug? Huh. Oh, I'm in the wrong micro also. Okay, that's the instruction I expected to see. Great. So, write assembly, branch. Oh, see, that's better. I think maybe the version for Raspberry Pi is just not good. Is there... Oh, interesting. That assembled. Ooh, IO cache. That seems useful. Let's try that. And... Hooray! Okay, so it's not my fault. The R2 on Raspberry Pi is just broken. Or maybe I was missing ARM and it was using something else. What was that? -A. Yeah. Well, I do actually want to run this on the Raspberry Pi because that's what I'm connected to with my hardware, so let's fix Radar on here maybe. your file is at the bottom of all this text. That is not the release I was looking for. There we go. Radar 1.4 source code. Let's grab a link to that. Oh, I guess I shouldn't use even the release. My gen in chat is saying that I should be using the one from GitHub. All right, I guess we can do that. Yeah, it's interesting. The release on my Mac was doing all right. The release on the Raspberry Pi was pretty having trouble with assembling. The cat's pretty cozy over there. Well, and that seems to be pretty much the patch we wanted. Well, if we have some waiting to do while this builds, then we could take a look at what's necessary to do for the other patch we wanted to try. Just this install script that that my gen is recommending. That seems pretty relevant. Sure. Sure, take over my little Raspberry. Oh, Radar is in the channel too. That's cool. Also, apt-get purge, Debian leaves traces. Good to know. Oh, and clone with depth 1. Yeah, I already cloned it, so I guess we're past that hurdle. Yeah, installing our backdoor. Yeah. Well, you can have all you want from my Raspberry, I guess, and try to make your way from here onto other computers. I guess we can do the apt-get purge over here. I mean, it seems like if I'm having a Raspberry on my robot, like that Raspberry should have the ability to edit the firmware on the gimbal. Like that just seems like a good idea. I mean, what fun is it having a reverse engineered gimbal on your robot if you aren't going to patch its firmware while it's flying? What was this? apt-cat or apt-get purge? I do have a pretty big SD card in this Raspberry Pi, at least. I think it's 64 gig. Yeah, we don't want any of that installed before the... Let's get rid of that before the new install actually happens. Oh, the Radar is warning me about a Debian GCC segfault out-of-memory bug. Oh, yeah, let's see if we hit that. Neat. cool, we can let that continue. And what is the state of our repo here? The state of our repo is the Raspberry Pi is starting to slow down. Or maybe I'm losing keyboard. Could be either. Okay. It's slowing down a little bit. That's fine. So this is, I guess this is doing multiple compiles. Oh yeah, there's all the compiles going. How is our memory doing? We have a little bit of free memory. Yeah, I mean, if this has trouble, I'll try running it again with make-j1. But it seems alright so far. Fingers crossed. Okay, so just to get our bearings here, currently the patches for MCUs 0 and 1 are empty. So I have a little script here which just unpacks the firmware, runs a Radar script on each of the binaries, then repacks it. And currently the patchers for the first two should be empty. Nothing yet. And for the pitch axis micro, we just have that one patch to jump over the whole follow loop, which should be straightforward, but of course, plenty of opportunities for stuff to go wrong. So while this is compiling, maybe let's look at MCU 0 and see how we can keep it in serial mode and prevent it from disabling the serial port. I think maybe we want to even go as far as having it know that the PC is attached, not just have it not disable the serial port. Even though knowing that the PC is attached does change the behavior somewhat. Oh, Sodium's saying the build script defaults to J12, which seems like a lot for a Raspberry Pi. I agree. Let's see how that works out. Okay, this is MCU 2. Let's put this away and go back to MCU 0. So I think the first thread we were pulling on here was just actually the command that you send during that little handshake where you say, "Hello, I'm a computer, please connect to me." And that was command B. Where was that in the actual jump table? Alright, so this has the two nested switch statements. Here's the second one. We're looking for case 11, command B, PC init. So this is the command that we'd already seen the kind of Windows software that comes with this Gimbal issue in order to keep it in serial mode so that it can send commands and read parameters and all that fun stuff. So this has to happen at a particular time. It has to be sent after we're done with the bootloader and we're in kind of the normal Gimbal firmware, but before it's actually finished booting up. So we should actually see a place in main where it's sending out one of these command Bs to the PC. And this is actually the response where, okay, the PC is attached. So all this is doing is setting a flag. It's setting this PC attached flag. I think what we want to do is just go back to the code that sends that initial command and figure out how we can put together a minimal change that'll cause that to just end up setting this flag and continuing on without having to wait. So if we look at where else this is used, it's affecting things elsewhere, like the follow loop behaves differently. Something in systic and time2, which are two timer handlers that I haven't really looked into yet. This is where we are now in the serial 1 handler. But it's also set here in main, or there's an access. Let's see what that is. So we're actually using this as a base address. This is pretty early in main too. So we're using this as a base address in various places. So some of this stuff, for example, I should actually convert this. This is not necessarily relevant to what we're doing, but it's kind of a cleanup task. Okay, this is actually the PC attached flag. I think R4 is preserved all the way down through here too. This is the loop where we are waiting for the PC to attach. This serial poll is, so we've already kind of stumbled on what we're looking for. So send packet to next MCU. This is, I think, sending on a successful connection to the next micro. So I think we do actually want to get here, unless we just make this change to every micro, but it seems easiest to only make this change to MCU 0. And so anyway, we'll come back here. I just want to finish setting these base addresses. Where was this? Yeah. Yeah, this register stays live with that same base for pretty much this entire function. It's pretty common with this compiler. Little critical sections here. This stuff that's poking at the watchdog seems a little iffy. I'm kind of curious what that is. Because they're actually like changing the watchdog speed in the main loop, which seems a little dangerous. But there's probably a reason for it. Okay, so back to the graphical representation of the main loop here. Oh, yeah, so you can see like right here at the bottom of the actual main loop, we just have serial polls. And this is probably some other related interface poll. Here, so where is this PC attached flag being used now? I have a few locations in main. Is this the first use? I think so. So this is the loop where we're sending out, these are the solicitations asking the host to connect. So we don't necessarily need this code, but if we changed this, then it would like break compatibility with some of the tools that are waiting for this command. So it would be nice to keep this intact, but perhaps only send one of these and act as if we got a response right away. And one way that we could do that is just immediately after sending this, we could just set that main flag PC attached to something. And I mean, it looks like if we just started up this function with the PC attached flag already set, then we would never send this to the host, which I don't think is what we want. So this loop runs multiple times. I think maybe it would make sense for this to send the command once, and then maybe down here we repurpose some of this, since I don't think we actually care about reading a response at this point. Maybe we repurpose this to be a set to write this flag, to set this flag back to 1. And then next time we go through this loop, we would send the packet on to the next microcontroller. So how do we decide when to repeat this? Is this just a timer? I kind of expect this may be just a timer. Like, are we going to find this incrementing in systic? Oh, that's just main. So this is a local variable, or at least local-ish. Let's assume this is a computer attach, like counter or something like that. PC attach loop counter for now. And where does this come from? This is set to 1. Is it always set to 1? I'll just call that usually 1, because I don't know what else it is right now. That's interesting. Wouldn't this skip this unless that's 0? Oh no, 0 is 1 up here also. This is probably just a flag indicating whether or not we should try to do the computer init. And maybe there's something in here that has the potential to set it to 0, and then we check it down here. So we're starting that out with 0. Then we're actually checking. And I don't think this is what we want. This would leave us in a state where the next microcontroller doesn't think that we have the PC attached, which I think is the state we want it in. I think we want everybody to know that the PC is attached. I mean, there might be advantages to having the PC attached flag clear on the other micros, like we could send joystick packets, but I don't think we care about sending joystick packets, since I'm going to patch out that joystick control code anyway. And then this counter increments. And we just have a maximum here. Oh, and I think this was a delay that we skipped over earlier. Yeah, this looks like this is a busy loop. So we could patch out, like we can overwrite these 3 instructions if we want to with our own stuff, since we won't need them. And then this will just end up, if we overwrite this busy loop, this might run too fast. Although I think this will be a no-op if the outgoing packet buffer is already full, so maybe that's fine. Oh, it waits for the packet buffer, which is also fine. So we'll send out kind of a burst of, hello, I'm still connected. So I think that might be part of what this does. I think this counter serves 2 purposes. One is to give us some time to wait for the PC to attach on the incoming side, and the other would be to spam out multiple copies of the, hey, I'm attached after the fact. Because, I mean, once we get here, once we're connected, we don't exit the loop. We just keep spamming out, hello, I'm connected kind of packets. So, like, a lot of this loop could be replaced if I wanted to. So I think we're getting a picture of how to patch this, and it looks like R2 finished compiling. And it looks like it installed too. Yay. Yay. Firmware, patcher, segfault. I think we fixed that by not specifying the .w. Yeah. B416. Okay. Let's you know, I'm feeling lucky. Let's make a patch for MCU 0 also. So something like that. Oh, nice. My gen also has a hint for trying out the fancy UTF-8 output in Radar 2. Let's try that. Let's go back in here without write mode. Oh, we actually do want the console. You crack me up. Thanks. Yeah, they totally got me with their little flavor text of "we're stealing your IDA key," because I'm like, wait, there is no IDA key on that machine. Completely fell for it. So, TF8. Ah. Ooh. Oh, is this from the current location, I assume? Oh, wow, there's like a scrolling happening here. Let's try this at a better address. Whoa. I'm not quite sure where I am, but it's interesting. So what was this? Ah, so that's the auto analysis. And then, what was this? Oh no. Visual mode. View graph. Neat. Let's go to a better address. I have that habit from, what is that, Windybug? I don't even know. B2BO. Nope. What was that command again? Ah, yeah. escr.utf8 is the part I forgot. R. Ag. Huh. That's interesting. Was the crash in the analysis or in the visual mode? I think it was in the visual mode. Oh. Is it memory related? Maybe it was something being set up to crash by the auto analysis. Jeffrey is asking if I can share the bin. I'd rather not share the binary directly, but it's really easy to regenerate this. So if you go to the Fayou Tech website, and products, support, and this probably works with multiple gimbals at this point, but the one that we've been working with is the Mini 3D. So you can just download any of these firmwares from the website. I've been using Gimbal firmware 1.5, and then specifically if you open this up, oh, why is this opening in VLC? Okay, well, in that RAR file you'll find a couple different firmware modes. There's one that says rocker position mode and one that's rocker speed mode, and I've been using the position mode. Yeah, imagine is saying do the scr.utf8 and the AAA only once. I don't understand what that is in reference to, because I was running Radar 2 multiple times. Anyway, I think I'm going to try to get back to what I was trying to do here. So I think I want to patch this block right here. Hello, keyboard. Did Sublime Text just crash? What is happening to my terminal? Oh, geez, what's going on? This just got super unresponsive. Oh, what is even happening? Let me try to SSH in here from elsewhere. It was VLC. There was a zombie process of VLC sucking up memory. Is this any better? Oh, yeah. Great. That's what happens when you open the firmware RAR file in VLC. It just sucks up all your computer's memory. Good to know. like that. Oh, this is nice. This is kind of the environment I wanted. Do my research wherever, and then have a little script that kind of recreates my patched binary whenever I need it. So 800 CC40. And then so we already have this R4 base address, which is super conveniently pointing right at our PC attached flag. So if we convert this back to an offset, we can see that it happens to be at base 0. So we just need to do like a write byte, and we need a 1 somewhere to write into it. Will this work with multiple instructions? Well, let's put a no up there. I think that'll be the right length, but we definitely need to take a look at that. That's interesting. Let's try to get to the bottom of that. Unpack. Oh. It's just seg faulting every time I do that. Sterling, huh? While printing something on the terminal with a bunch of color codes. Formatting the disassembly comment. Can I avoid this somehow? Can I avoid this by printing a smaller window? I mean, if the problem's just in printing, then I can still do my patch, but it'll be harder to know what's working. Oh, it looks like some suggestions in the chat that I'm behind on. Yeah. Well, I guess we could try running this elsewhere. I mean, we could also just try our patch to the second micro and then come back to this. I'm also tempted to comment out the print and see if we can make it any further. Well, let's see what that did. Maybe I can disable the console colors. Is that maybe related to the issue? Does it disable that automatically? No. Well, let's just see if this worked. So, just get a clean output from this. And then, is there an R2 disassembler? No. Let's just try opening this again. CC40. That time, what did that do? Where did I get that muscle memory? Maybe I'll try turning off color. No, that wasn't it. How much disassembly can I do before it crashes? Oh, that's B1. That first instruction is causing the problem. Maybe I'm just writing this wrong. I mean, move S is kind of what I wanted, but it couldn't assemble move S. Why couldn't it assemble move S? Yeah, so that's not an instruction it knows. Is it? Is it move S dot? Ow. What does this look like in disassembly? Stereogram. That's funny. Bits. Oh, PX is print hex. There's so many cool options though. Is that not my entry point? Oh no, I think it does start with no ops. Yeah, so that looks fine. Can I find any? Try PI. For what? Oh, print is that for instructions? Oh, gotcha. Okay, yeah. This was the instruction I was having trouble with. Let's set the block size to something smaller. Oh. So that was writing it as move, and then it gave me a move S. Okay. Okay, okay. I guess that's the thing. So this needs to be move, and this maybe PI won't crash. Oh, let's comment out the ones we're not using. Okay, so here's an example patch. We have this move S, and that's it. Let's see if this looks like what we expected. So that wrote over this move S, and we've got these same BLs. Okay, cool. Can we do more patching? Looks like these had no effect. What is the way to write consecutive instructions? Quotes. Okay, we look like we get one more NOP, because I need to have bytes here. Number of opcode bytes for, great. So yeah, these are both double width instructions in thumb 2. So we can overwrite this with one instruction, then we overwrote this with 2 instructions. Now that gets us to here, which we could leave that intact. Yeah, there's actually no reason not to overwrite that, but it seems maybe a little safer to zero that one out too. It doesn't really matter that much, but let's just put another couple of no ops in there. So now we've got no ops up until this load, which is this one. Attach loop counter, which should have an offset of 8. Great. I think this patch will give us a gimbal that always starts up in serial mode. Oh, that's a good suggestion from Robert, to patch only serial 1 pole and leave the delay. Do I want the delay? It would be safer to leave the delay. I don't know that I want it. I probably don't, but it's safer to not delete it. Sure, so then we'd be writing here at 800cc40. Or 46. This will actually operate very, very similarly to the original code. It's just instead of checking the serial port and polling, we just end up setting the same flag. But it ends up setting the same thing at the same time. The only difference is that we don't end up processing other serial commands if those happen to come in. And then we want to get rid of both of these, right? Okay, so now we're patching a different location, CC46, which is right here. So instead of that BL, we now have a move S, a store B. Then right after that, we have the LDR, add, store, etc. that we had before. That seems good. Another suggestion from my gen, check WAO. I'm trying to parse what that is. Oh, that's a command. It was kind of hard for me to tell what the text was in the window there, but. Ah, modification. That's handy. Yay. You can be like, wow, nop. Wow, nop, 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 nop. Wow, trap. Yeah, no, that seems great. Seems super useful. And yeah, returning might be useful in the future. Right now we're just, like, there's so much inlining that, like, functions tend to do a lot in this firmware for the most part. Oops. Okay, so we've got that. Let's test this. Patcher, patcher, patcher. So we have our assembled binary. It is definitely different. So we have a different header. Then there's this block right here. You can notice that the differences start on a SHA-1 block boundary, so 16 bytes, and then they continue until the end of the 1024 byte block boundary. All right. I think I'm just going to flash it. So let's turn the camera back on. Live bricking session in progress. All right, so it is operating normally now, following and everything. Look at that, happy gimbal. So power off. FY flash firmware / assembled.bin. Flashing. We could have this flashing only the change blocks. Pretty windy outside. All these identical blocks where the firmware is not happening. You know, at least the good news is I probably don't have a way of totally locking myself out of the bootloader super easily. Like, I'd be surprised if I come up with a way of, well, I shouldn't jinx it, but it seems like the bootloader runs and then totally transfers control here, and I'm not relying on ever having to explicitly exit from this firmware. Okay, so it's written. If I reboot it now, what I expect to happen is that the gimbal should stay limp. It shouldn't power on the motors. And then if I run one of these other programs after powering it on, it should still connect, whereas before it wouldn't have, because it would be in PWM mode. So, power cycle. Well, so far so good. It's dead, which is what I was hoping at this point. Let's see if we can talk to it though. Paramdiv. Oh, look at that. We are so communicating with this gimbal now. Let's give ourselves enough room to actually display this. This is good. This means I don't need a load switch for turning on the power only after I have the serial endpoint running. Yeah, that looks pretty live. All right. So man, that's great. I'm happy with this so far. Let's try the controller. Let's get the Xbox controller over here powered. So as soon as I run this, it should power on the motors. There it goes. I have steering. So that's great. So we did what we wanted on MCU 0. We haven't broken the other MCUs yet. The change that I made on MCU 2 should give us control over the pitch adjustment. So what is the pitch doing right now? I expect right now the pitch to not do much. I guess it's following front. Okay. Whoa, a little bit of yaw instability there. Okay, let's open the grapher. That's where we will see the rest of the parameters we need. All right, so if the change we just made had the effect we wanted, what I'll expect is that this follow mode for the yaw or the pitch axis should no longer have any effect. And if I adjust the control rate for that axis, then this should actually work now. So, and the X control rate is hooked up to the joystick right now. So if I move the joystick, you'll see the X rate changing. But nothing should be driving the pitch rate right now. It works! Oh, come back. No. Okay, it's a little tough to respect the end stops manually, but yeah, that's working. Let's hook the joystick up to that. Maybe turn the motors off for the moment. Cool. Controller. So, let's change this comment to reflect the current reality. Cool. That's much simpler now. The pitch limits. How are we going to do limits? I don't know what coordinate system. Oh. That's going to be in param 8. Will have the current pitch value, so that's cool. Yeah, I don't quite know what coordinate system this is going to be in, so I'm going to give it some pretty wide limits for the moment, but then we can narrow that down. So wait connect. I'm not gonna, this will happen automatically now, so that's fun. So follow loops are all off. 0 the velocity output. Okay, and we will no longer be doing this local pitch integration. That was kind of a hack. And now I think I want these to have a similar nonlinear control. No more sending joystick packets. We can be done with the joystick packet nonsense. So the current yaw is measured using the angle sensor. I'm going to use the pitch from parameter 8. So that should already be relative to the horizon. So we're asking for the current state from the pitch microcontroller. And that is not great, but we can fix that later. So we could set vector here, but I think I'm going to set only the yaw and pitch and leave the roll alone in case that is fighting the roll micro. And is that all? Oh. Huh. Did maybe that zeroing of the speeds not send? Anyway, I think the root cause is this error. There might be some error handling that needs to change. Command pitch. Command, oh, current pitch. This should be, and this would be command pitch speed. Okay, and if I do power up the gimbal after running that, then that's fine too. That's cool. Okay, I think that's backwards. Also, that pitch estimate from param 8 only seems to update when we're steady, or when we're stopped, which is interesting. We might have to find a better readback to use for that. I'm just going to change this to like -150 because pitch is way too fast right now. And see, I can start this up and it doesn't move at all. Like it keeps its previous heading. I think we should look at the video output from this. I bet it's going to look good. sure this control could use some tweaking. Me too. Hey, buddy. What do you think about Gimbal's little cat? All right now. How about that? The large dead zone is a little bit too big, maybe. It means it's hard to move it diagonally. It's much easier to move it in a straight line. Having it be like a vector dead zone instead of a linear dead zone might make that a little easier. Oh, this is great. Let's just make that camera full screen. Can steer this around. Hello. Here's me. So I do want to have a limit about how much upness you can give it because the motor gets a little unstable past a certain point. That's about fine. Roy asks, have you ever tried taking the IDA ASM, creating a C project, and starting out with inline ASM for the methods? You mean to make a completely reassemblable version of the program? There's usually a lot of work necessary to take a disassembly from IDA and make it reassemblable. It's not necessarily what they always intend, but one thing I have done is I'll just make a standalone project using, GCC or GNU ASM or whatever, and then have a linker script that places the chunks of code I want at the right locations, and then I'll just have like an ELF file that I can overlay on top of something. That's what the tools that I wrote a while ago for patching the Nintendo DS ended up doing. But that was a lot of infrastructure. That was something that I couldn't just do super quickly. That was like a tool that I built. A little bit of jerkiness here seems to be on the video rather than on the gimbal. It might be like a frame rate issue. Got a little bit of wobble in the yaw axis. If I like swing back and forth. But yeah, this is feeling pretty interactive. This is all based on reverse engineered commands and patched firmwares. So, can we move around the gimbal? Because that would be a nice additional test to do with this to make sure that, this can handle user input and a moving platform at the same time. So I'm just going to pick this up. Maybe let's get the camera overlay so you can see what I'm doing also. That seems to be doing what I want. The follow loop is totally disabled on both of those axes. But I can still manually point it. Oh, there's some shimmy. That's going to need some calibration. And I don't know actually what the best way to calibrate that is. Like, is that a gain problem, or is it a problem in the offset calibration that we did earlier? That could be something to look into. But I'm really stoked about not needing a power load switch now, because I thought I was going to need to build like a little power distribution board that lets me turn on and off the gimbal in software. But now I can just do that over the serial port. Yeah, a little bit of horizontal wobble. I'm going to be mostly looking down, though, because this is going to be a hovering robot. It's going to be spending more of its time in this kind of position. Still got the yaw wobble in this position. Anyway, I think this is about the wrap-up point for this stream. I feel like we've got a pretty, made some pretty good progress on this. We have a binary patch to the firmware that kind of sets the mode the way we want it to be. And maybe a little bit of tuning to do on that yaw axis. So we could just kind of start doing that blindly. We could actually try to figure out where the PID parameters are. It might be worth spending some time in IDA looking at what uses that param 8 that seems to be the integrated output of this control loop. Oops. Yeah, I think I need to understand param 8 a lot better, because this thing where it only changes when the gimbal is still is not super useful. I need to find a pitch estimate that's reliable while the gimbal's moving. Robert is asking again if I'm going to make a boot ROM dump. No. Yeah, that wobble in the horizontal is definitely a problem. Not a huge problem, but a problem. But now I'm imagining giving this thing a closed loop with a computer vision system. Like, imagine having this thing track a particular object even as you move it around. Like, we have the input for that now. That's super exciting to me. Steer this thing around. Hey Tuco, what do you think about the stream? It'd be nice if I could get Tuco in the Tuco cam right now. How many wires would I have to move to get that to happen? I could simplify this setup a little bit and run the Raspberry Pi off of a power bank, but I think I'm going to save that for after I have a little more design on the robot, since I should just do that. This seems quite gimbally. And while this program is running, actually, we have access to that other parameter UI, so that would be a good point to start out with for tweaking. So this is running. You can see that current on the left is the. I guess I could just use the magnetic encoder for pitch also. I don't know if that's exactly what I want, but because if the whole platform is tilted, then I don't really necessarily want this to be that angle. I want it to be the angle between camera and horizon, but I don't know that it matters that much, because usually it'll be pretty planar. So if I move the yaw, you can see that moves continuously, because that's just reading the magnetic encoder directly. But if I move the pitch, so you can see the camera moving right away, but the thing next to command there, which should say current, that's a bug, the thing that should say current only changes when the gimbal is stopped. So it'd be nice to find a different number to use for that. This little UI is still in operation if I at least reload the page. Hello? There we go. So as I move this around, oh, interesting. When it went all buzzy, this green motor power swung all the way over like that. It's interesting. This is looking more like 6F is actually power, and 70 might be some like position. Maybe 6F is torque and 70 is a location estimate. Oh, these are a little bit off the screen. That's what I'm talking about. Oh, maybe the gyro angle is what I want. Because that's the camera versus the horizon. Oh, yeah, that's what I want. That updates right away, and it's pretty smooth. Yeah, okay. That's exactly what I want. The gyro is number 9. Let's try that. Oh, that's nice. And 0 should actually be the horizon in this coordinate system. Yeah. That's great. So now I can just have my own servo loop move this with the speed that I want, or try to hit a particular position, or whatever. It's up to me now, which is great. So I've got speeds out and positions in, which is great. Yay. Well, folks, I think that's about it for this. If you want to play along at home, as always, we've got the files, at least the files that I created in GitHub, and the firmwares you can download. Go to scanlime/fy gimbal. The controller that we were just running is this script right here. And the binary patch now is in firmware. You can find some scripts for packing and unpacking the firmware blobs, and these little Radar scripts for the actual binary patches that we just did. Yay! Oh, Mike is asking, did I already turn up the baud rate? Is it unnecessary at this point? I did not. It's probably unnecessary. We could. It's certainly an option. It'd be easy to do. At this point, it seems slightly preferable to maintain compatibility with the other firmwares, at least insofar as I care. So I'm not going to necessarily turn up the baud rate, although if we need to, I'm sure it'd be really easy to actually do that. Yeah, good question. Well, I think that's pretty much it for this stream. Thanks for tuning in, as always. Happy we got to cover so much ground and use a variety of tools here. It was nice using Radar in addition to the usual IDA here. Maybe next time I'll have my slightly less crufty Windows VM running this. Let's have a moment of Tuco before we wrap this up. Cat is in cleaning mode. Cleaning mode activate. Cleaning mode 10% complete. Well, thanks for tuning in, everyone. As always, more updates to this stuff as it happens, in the chat, on Twitter, or wherever else it happens. And looking forward to having this robot actually able to interact with the cat in real time, anytime you like. That'll be nice. Happy hacking, everyone.